Hello and welcome to International Geoscience Colloquium, jointly organized by Christ College Autonomous, University of Kerala, University of Exeter, University of Zululand, South Africa, supported by Ministry of Earth Science, Government of India. Here we are on the final day of International Geoscience Colloquium. We have participants attending the program through Zoom and YouTube live right now. And meanwhile, we'll be also having a validity function at 4:20, from 4:20 to 5:10 Indian Standard Time. And we have some interesting presentations waiting ahead. Without further delay, let me invite our session chair, Dr. Saju Menacheri, to take over the session. Over to you, sir.
Saju, you're muted.
Thank you. Sorry for that. Welcome to the virtual International Geoscience Colloquium Session 3. My name is Saju Menacheri, a reservoir quality geologist, together with Zakaria John, geomechanics team leader, Slambaja, Australia. We are the session chairs for the technical session 3, development in stratigraphy and sedimentology, big data analytics and artificial intelligence in geosciences, geoscience and integrated reservoir modeling. I would like to invite my co-chair to start with the speaker's introduction and to the further proceedings. Thank you, Zach.
Thanks, Saju. My name is Zach John, and I will go through the first item on the program. In this session, you will listen to 3 presentations covering the various aspects of the topic, and a valedictory session will be later on. Each presentation will be about 30 to 40 minutes. At the end of each presentation, you will have about 10 minutes of question answer time with the speaker. This session is on big data analytics and artificial intelligence in geosciences. I would now like to introduce you to our first speaker today, Mr. Johannes Novara from Jakarta, Indonesia. He will be presenting on the subject on machine learning in subsurface analysis. A little bit about the speaker today. Mr. Johannes is now working as a reservoir geophysicist. He had BSc in geophysics from Bandung Institute of Technology in Indonesia. He has achieved outstanding achievements, one of them being a CO2 challenge by Equinor and EAG in 2019. He was awarded the most outstanding student in his department and 2 campus awards for outstanding students in the consecutive years of 2018 and 2019. He had several high-rank publications. One of them is about integration of rock physics, time-lapse seismic modeling, and geomechanics for CO2 storage, which he will present in the 82nd EAG annual conference next year in Amsterdam, Netherlands. He worked for Fukuda Geological Institute in Japan to develop time-lapse seismic modeling and seal analysis techniques for underground CO2 storage in carbonate formations. Presently, he has been teaching Python courses for professionals and academics worldwide with the Society of Petroleum Engineers. He has experience in solving geoscience and petroleum engineering challenges using Python programming language, and is currently developing Python utilities in GitHub. In the machine learning domain, he wants to integrate Python workflows for reservoir analysis with multiple disciplines to solve complicated problems. So please mute your video and microphone all the time until you have a question to ask during the question answers time. When you're asking the question, please unmute the video and your microphone. Please enter any question you may have in the question answer chat box at the right corner. You may enter question during the presentation itself. You do not need to wait until the end of the session to enter your question. So we now welcome Mr. Johannes for the talk. Over to you, Johannes.
Thank you, Dr. Zach John and Dr. Saju Menacheri. It's really interesting for me to be here to attend the International Geosciences Symposium. So first of all, I'd like to thank you for the committee for inviting me in this very, very interesting session. And hi, everyone. Thank you for attending this presentation. Today, I would like to share about some application of machine learning in reservoir subsurface analysis. But today I would like to specify for our discussion about a prediction of sonic log for a better prediction and making lots of mechanical models from that. So first of all, I'd like to share my screen. I have prepared the presentation here. Okay. So
yeah, we can see it.
yeah, thank you. Okay. So this is the first, the introduction to machine learning application subsurface analysis case study in the North Sea. Actually, this is my current project. I have made some projects related to machine learning in the North Sea. And actually, North Sea data is a really massive data that we can access in the website because it's really open for all researchers and professionals. And one of the data in North Sea is from the Pole field. We can see lots of data in the Pole field, and if we apply machine learning, we can get lots of insights and produce many things, many interesting things that we can do to enhance our interpretation in the subsurface analysis, and lots of challenges that we basically do and come across when we are doing such this analysis in our workflow. So the outlines of today's presentation, I would like to give a brief introduction of what is machine learning and what is really exotic about machine learning. And then I would like to bring the machine learning into the geoscience. What problems or what topics in geosciences that machine learning can contribute and apply. And then using our basic understanding in machine learning, I would like to share you the workflow, the very basic workflow that machine learning can do for the reservoir analysis. And then I will bring to the case study, which is the Pole field in the North Sea. And then I will explain one by one, step by step, how to do machine learning in reservoir analysis, started from exploratory data analysis, pre-processing, and finally we do the prediction. So actually machine learning, 70% of machine learning workflows are the pre-processing. And when we do the prediction and we got a new model, this new model really depends on our data and our pre-processing. So 70% of the machine learning workflow is the pre-processing. If we do the pre-processing very well, we can make a really good model to predict anything in the reservoir. So what is machine learning? Machine learning is basically, this is an algorithm, and these algorithms are done using a computer or a simulation or the algorithm. And this algorithm assisted process will give us a prediction, and the way it predicts and produce a new model to predict a data, it learns through a data as an input. And then from this data, from this machine learning, the algorithm will train the data. And then after it trains the data, it has a model. And using the model, basically this is a mathematical model. We, in our college or industry, we are developing lots of mathematical models, but here in machine learning, this model is called the predictive model. It means that this model can predict something out of the data. And then after the data is being trained by the machine learning model, it finally outputs a prediction. Maybe, for example, we would like to get facies distribution in our reservoir. So there are lots of data that we gather from the field, for example, the geophysical logs or seismic logs. These are the data. And then when we do the machine learning, we make a model that trains the seismic or geophysical well logs. And then from this data, we can apply this model to predict, for example, some properties like acoustic impedance or mechanical properties or anything else we can produce using machine learning. And then these are some applications of machine learning in geoscience. We can generate a new data that is called the prediction or regression. And then we can generate facious models from this geophysical logs. And then we can also do a clustering. For example, we have a data, or we have geophysical well logs, and it doesn't have any facious labels. We can make our own facious labels using what is called as unsupervised learning classification. There is a difference between unsupervised and supervised. So after this slide, I will explain what is the difference between unsupervised and supervised. This is really important. If we don't have any data, we use unsupervised, or we don't have any labels or any facious models in our data, we use unsupervised. And also, we can also do the fault identification in the seismic 3D data. And we can also identify or spot an anomaly in our seismic data. This is really, really popular nowadays. Some researchers are developing a model that can identify faults in a seismic data. And commonly we interpret the seismic data. It takes long time for days or even for weeks. We interpret the faults in our seismic data. And maybe there are lots of complexities in the faults. For example, a really complex fault model. And these researchers are developing a model that can see this anomaly, and then it can give us what is the probability of the faults inside our seismic data. And also we do the rock typing, and it uses what is called as self-organizing maps. This is a type of neural network. So basically, these are several terminologies that geoscientists and maybe non-machine learning experts have to understand. Okay, so the first two terms here are the classification and regression. The difference is that for classification, you would like to, for example, you'd like to generate a facious label. So we can classify whether this cluster or data points are attributed to certain facious models, and other data points are attributed to facious models. So we can have lots of facious models in our data. But for regression, it means that we would like to produce new properties. For example, I would like to produce acoustic impedance from the geophysical well logs. So it predicts the acoustic impedance from our data. So it's called the regression. And also, what is called by training and testing. This, if we have a data, we will separate this data into, for example, 80% for training and 20% for testing. And for this clusters of data that we categorize into training and testing, we train the data that is in purpose for the training. We train this data, and then we build a model. And then for this model, we apply to our testing data. So before machine learning workflow, we have to divide data into training data and the testing data. Actually, there is another category that is called the validation data. So we can also divide the data into three categories, and then we train the data, and then from after we have the model, we would like to validate if this model is a good model to predict. So we test the model into a validation data, and then if we have a very good model, we can directly apply to our test data. And then there is a difference between supervised and unsupervised. Maybe here I would like to show, this is a pictorial representation of machine learning. Here we have density, resistivity, gamma ray, and formation. These are our data, and also the P velocity log. We have this data, and then for maybe we have another wells that we don't have a DD or the compressional velocity log there. And our machine learning task, we try to make a model from this complete data, and then from this complete data, we build the model, And then from this model, we apply to the wells that doesn't have any DT log or compressional velocity. So this task is, if we recall the terminologies, it's a regression task because we would like to predict a new variable for our data. It's not a classification because here the true, like we have this DT log. If we have not the DT log but facies labels, for example, these facies labels, this is attributed to sandstone or shale or carbonate. This is called the classification because we would like to classify this data into these three lithologies. And then we are dealing with features and target. So features are all the data that we will use for our prediction, and our target is the one that we would like to predict. So for example, this one's density, resistivity, gamma ray, and formation label, this is our features. And this one, the true DT log, this is our target. And also this is the observation. So if we read here row by row, this is observation number 1, and also so each recorded depth, it has each observation. And also we are dealing with continuous and categorical. What is the meaning of continuous? It's the numbers or any variables that has numbers, float, or integers. But for categorical, we have, for example, some names here in the formation, Heather, Hugin, and Sleipner. This is a formation in the North Sea. So we can categorize this as the categorical, and then this one as the continuous. And also we are dealing with non-numerical values. For example, here we have some missing data here. This is what we call as the non-numerical values. And our task before we do machine learning, we have to impute this missing data. So after we impute, we have this new data. Maybe some people prefer to delete some observations that has missing variables, but it's not as acceptable because if we have really small volume of data, if we delete some observations, we don't have enough data for training. And also from this, we measure the accuracy, and then we can see how accurate our model is. Okay, so actually this is the really basic workflow. We start from the feature, and we do the exploratory data analysis. This EDA is for finding out the statistical distributions or other properties in our data. And then after we know exactly what is being contained in our data, what is the distribution of our data, what is the correlation in our data, we select which data is suitable for our features. So we do the feature selection and feature engineering, and then we do the data normalization and removing outliers. These are the critical steps because if our data is not too normalized, we don't have a really good enough model for our prediction. So we have to normalize our data, and then we have to remove the outliers in the data. And also, after that, we split the data into training and testing. Before, I've already explained about the training and testing. So we split this data into train and test, maybe 80 or 20, or maybe 70, 30 for training and testing. So we split the data, and then we do the first training and prediction, and we compare. So actually, machine learning is really understandable. We just like we have a data here, and then we have a data here. We create a model, and then we apply to a data that has already has the data or the target. And then for this result, we compare is the predicted result matches with the true result. And from this examination, we know that is it a good model or not. If it is a good model, we can directly apply to our data that has a missing data. For example, in this case, we missed our DD log. But if we don't trust really our data, we can do what is called as hyperparameter tuning, or in mathematics, we know it as an optimization. And then after we have a good model, we do the final prediction and we come up with a final predicted result. And this is a brief introduction to the full field. So there are 5 wells in the full field. Maybe there are lots of wells there, but for this workflow, we use the 5 wells, and 3 of these 5 wells have DD log, but the other 2 logs doesn't have a sonic log. So our objective now is to predict the DD log for our wells, well 2 and well 5, that don't have a sonic velocity log. And this is the training data. You can see here the this neutron density up to the caliper. These are our features, and the DT log, because this is our target, so we call it as target. So from NPHI to caliper, we call it as features, and then the DT log is our target. And here is the testing data. We don't have the DD, right? Because it's the test data. So we don't have the DT log, because in this well, we would like to predict what the sonic velocity log will look like in this well. So first of all, this is the exploratory data analysis. Before we are doing machine learning, we are learning the statistics in our data. And the way we do the exploratory data analysis, we use the pair plots. Actually, pair plots is really powerful to represent our data, because it provides us a kind of intuitive way to analyze our data and to identify distributions or statistical distributions in our data. And if we want to look at the multivariate distributions or univariate distributions, we use a pair plot to use that. For example, here this is a pair plot of this data. Here we have all of the features here, and this is our target, the DT log. And from this pair plot only, we have several observations. And from these observations, we will decide what is the next best method we have to apply to solve some challenges. Here, for example, in this, we have a spike distributions. Why? Because it is RT is our resistivity. And for petrophysicists, we analyze the resistivity if we can transform it into a logarithmic plot. So for B here, because it doesn't have a logarithmic distributions, it appears as a spike distributions. And from here also, we can see some data is not Gaussian distribution. It is a big problem for machine learning, because machine learning prefers for the data to have a Gaussian distribution. So for this A later, we have to do a data normalization. And then we can see several correlations here. E is positively correlated, and maybe here, G is not correlated. And then we can also use the heat map to visualize the correlations of our data. There are 2 basic correlation methods. We can measure it with Pearson and Spearman correlation method. And the way the heat map looks like is like this. We have this one is our features, and this one is our features. And we can see here in this box, we can generalize which features are positively or positively correlated with our data. Here we know that this neutron density, gamma ray, resistivity, and photoelectric, these are correlated with our data, but this one, the caliper, is not to correlate with our data. So for machine learning, it is best to phase out this caliper log, because it's not too correlated, and we would like to predict. So we have to use features that have a correlation with our target. And then we also deal with missing data. Before I show a diagram of a table that has several missing data, and there are 2 methods or 2 ways the way we do with the missing data. Either we drop all observations that have missing data, or we can impute. What is the meaning of imputation? We produce, or we produce a new value for this missing value. For example, we get the imputed data from average value, or from the mean value, or any specific value that we want to impute the data. Here, using this exploratory data analysis, we can see some data are missing here. So this is a really, really powerful tool. We use the exploratory data analysis to analyze our data and what things we have to improve, or what things we have to solve before we do the machine learning. Because machine learning won't work if we have this kind of missing data. So we have to, maybe we have to apply a certain cutoff here, where all the depth intervals have all the data. And then we do the feature engineering. When we see here, previously we have here the B1 is the resistivity distribution. We have this spike distribution. We have to transform this resistivity into a logarithmic. So we do feature engineering to transform a feature that has not really good distribution. This is called the feature engineering. We can do other feature engineering. For example, we can generate our own features from the spatial coordinates X, Y, Z. If we handle with distributions of the phases in our reservoir, because it has a constraint of spatial constraint, we have to produce the spatial features from the X, Y, and Z from our trajectory files. And for some people, they develop these features for themselves, and then they can improve the machine learning for their specific purpose. So this one is our data after we have already engineering our feature here. This is the resistivity before we have the spiky distributions here. Right now we have a more Gaussian look here. So this is the result of the feature engineering. And we do the data transformation because some of our distributions are not so Gaussian. So we transform this data using normalization or standardization. We use some methods, for example, the power transform, regularization, standardization, normalization. And basically, when we do the data transformation, we compare which method of data transformation that best fit for our purpose. And maybe we come across here, we have the standardization as our first method here. So we have, this is not so Gaussian, but if we apply another transformation method that is called the power transform or Yeo-Johnson method, we can see here the distributions is more Gaussian here. And also for here, the gamma ray is compared to this one. The gamma ray is not so Gaussian here, but after we transform it into another transformation method, we can have this kind of Gaussian looks, and this one also for DT. And then we have to also remove some outliers in our data. Also, there are lots of removal outliers. For example, we can use the simplest one. We use the standardization, and we use the standard deviation and the average value to identify outliers in our data. And there are lots of methods here. For example, we have isolation forest, minimum covariance, LOF, and one class SVM. Also, we compare these methods and which method is the best for our data. And for example, here, we have the best outlier removal method using one class support vector machine. And if we compare this with our previous one, we have here lots of outliers, and these outliers have to be removed. And after we apply with this one class SVM, we can have these outliers are already minimized here. And this is our data that is already prepared for machine learning. So without doing this data normalization or removing outliers, we cannot do machine learning. We have to make a perfect data for our perfect model. And then we do the prediction. And these are the models that we use for regressions. We have nearest neighbors, support vector machine, decision tree, random forest. Actually, there are some mathematical foundations in understanding this model, but each different model have different kinds of algorithm to predict the data. Here we can have the different behaviors on how several methods are clustering our data. For example, the nearest neighbor here and the support vector machine here. I can say that this is the best for our data because it can cluster the data using a certain polynomials methods and the decision tree random forest. And we have to compare also these methods, which one is the best for our data. And for the first attempt, we split the data into task and training data. And then we trained our models. If we have like here a linear regression, self-support vector machine or decision tree, we test these models to our data. And then we print the metrics to evaluate the performance of each regressor so that we know that is this model accurate to predict to our data or not. And then these are the results here. We use the 6 models: linear regression, random forest, support vector machine, decision tree, gradient boosting, and nearest neighbor. From this, only from this metric, we can see which one is the best for our data. And of course, if we see here the gradient boosting here, we have the R-squared and the RMSE. This is the root mean square error and the R-squared error. So for this 2 metrics, we know that this one is the best model. Actually, a random forest here is better than gradient boosting, but we can actually, if we trust one model, for example, I would like to take gradient boosting for our model, for my model, and then for this gradient boosting, I can still improve my model using what is called as hyperparameter tuning. And for this study, we use the gradient boosting because some people prefer to use gradient boosting because it's quite robust for a predictive model. Many people who wins a competition that is hosted by several companies, they use the gradient boosting to predict a data. So for this gradient boosting, if we have this 0.95, we can still improve it using hyperparameter tuning. And if we compare here, this is our true DT log and this is our predicted DT log. Here we can compare how close they are. Maybe here it's not so close here. So we can still improve this model. And then for this well 3 and well 4, we have this comparison. For true versus predicted DT log here. Okay, so this is the model have already trained the data, and then it results here the predicted DT, and then which one is the best? So for this study, we pick the gradient boosting as the model to predict our data, but also we can improve this model by using what is called as hyperparameter tuning. Basically, hyperparameter tuning is a kind of mathematical optimization. If we have some kinds of objective function, we would like to optimize this objective function so that we know which parameters are the best for our model. And basically, each model, for example, SVM or other models, they have certain parameters as their inputs. So we use the optimization to search the most optimum input so that our model can perform the best for our data. Here for the gradient boosting, we have actually two inputs: the number of trees and the number of leaves. So this there are lots of inputs for each model, and we would like to optimize. And the way we are using optimization in machine learning, we use three methods: the grid search, randomized search, and Bayesian optimization. If we compare these three methods, we can see that Bayesian optimization is the fastest one, but we cannot guarantee that the fastest hyperparameter tuning can improve our model. So commonly we use a grid search. It can take longer time, but it results a good improvement to our model. Here we can compare these hyperparameters if we don't tune the hyperparameters. So this is our previous metric, and after we apply the hyperparameter tuning, we can see the improvement here. So from 0.95 to 0.98. So this is the improved model, and using this improved model, we repeat again our workflow, and we redo the prediction to the data. And then after we have a good model, we can apply this model to our data. So it's kind of iterative task. When we do the machine learning, we have to assess each time whether our model is good or not so good for our data. So this is the result using our tune model. We have this our features, and this one is our predicted DT. So this one is our result of our prediction here. So this is one of the wells that is in the fault field. So we have predicted the DT log from this sets of geophysical logs using our tune model. So what we get from our experiments and our workflow in machine learning, the conclusion is machine learning is actually, I would like to say that machine learning is not everything. We have to every time consult with domain expertises in the field, and either we can make this model, or is this model acceptable for our data, because maybe there are lots of anomalies that we come across in our data. For example, in the petrophysics, we know the borehole invasion or the effect of the salinity, effect of salinity in our logs. So we have to take into account this kind of considerations before we decide which model that can predict a new properties in our data. So for this data, we have already predicted the sonic log in our data, and then we can improve the model using hyperparameter tuning. So to say that machine learning is the future, and I'm really glad to see lots of applications in machine learning and lots of applications in geosciences. For example, seismic fault identification and facies models. So I still await for lots of developments in machine learning developments, so that in the future, if we have some problems or some challenges in reservoir analysis, we can use machine learning to assist our task and to do a better prediction, to assist our workflow and to calibrate with our results. So thank you for hearing my presentation. So I'm open for questions for this presentation. Thank you all.
Thank you, Johannes. That was a very interesting presentation. You walked us through a number of concepts. So we are open to questions, and anyone having any questions, either you can type it in the chat or you can unmute yourself and ask the question. While we are waiting for others to join in with a question, I have a question, Johannes. I remember hearing quite a bit about neural networks. How was, and that was being used a few years back. How is neural networks different from machine learning?
Well, actually, neural network is one of the methods in machine learning. So the methods or the models that we know in machine learning are the classical ones. these models are the mathematical models. This is the classical model. We know in mathematics there are mathematical models. For example, support vector machine is a mathematical model, but in neural network, it is not so mathematical. It is also stochastic. So in neural network, we have to build neurons, and then from this neural network, we predict. Actually, neural network and machine learning are the same thing, but the way these two models predict or classify the data has different kinds of algorithm. In neural network, there are what is called as back propagation and forward propagation. So so the neurons in the neural network, they train the data and then they propagate back and then forward and backward. So there are iterations in neural network. And actually, if we compare neural network and machine learning, we have to assess whether, for example, we would like to compare support vector machine model with neural network. So as always, we compare these two models, and we print the matrix as always, and then we can decide which one is the best for our data. And for complicated tasks, for example, for fault identification, if we use the machine learning, for example, support vector machine, it is quite long time to train the data. So we use the neural network because it behaves stochastically. It can take shorter time, but we have to also apply what is called as the learning rate or other variables, and we have to specify these variables. And we see the learning curve. If the result converges, so we can say that this model can predict a fault in our seismic data. So actually, this is really interesting to see the neural network application, because neural network application is really robust to be applied in rock typing, seismic fault identification, and lots of, like, for example, we would like to specify the phases in phases model for our stratigraphy. We can use the neural network to predict these things. So it behaves more stochastically. So we use the neural network to do our prediction.
Yeah, thanks, Johannes. We have about 7-8 minutes more. Any other question?
Thank you, Johannes. I have a question.
Yeah,
Hello?
go ahead.
Yeah,
Yeah,
sure.
go ahead, Raj.
Yeah. Can we identify a particular pattern in log using machine learning in particular for finding and seeing the distribution of different phases in particular formation?
Yeah, we know in sedimentology and stratigraphy we have electrophases. For example, we have different shapes for different depositional environment. We can use the what is called as convolutional neural network. This CNN is a really popular method to identify the pattern in the geophysical logs. So this CNN model, it can identify whether this log is bell-shaped or serrated, and then if after the CNN model understand the pattern in our data, and then we give another new data in our for our model, it can predict whether it can predict from the pattern there in the another data. Is this fluvio-deltaic or other depositional environments in our data from this pattern? So yeah, so one of the methods in machine learning, what is called as convolutional neural network, CNN. So it's again neural network, because neural network is a quite robust method to see patterns, anomalies in our data. So CNN is the most popular one, I think, for identifying patterns in our data, and also anomalies. Also for maybe, for example, we are dealing with salt body in the seismic data, and we would like to classify different waveforms in the seismic data, in our seismic data. So we can use the CNN to scan the seismic data, so it can classify whether this waveform is attributed to certain phases and another phases.
Thank you. Thank you, Ivan.
Johannes, I got a question for you.
Yeah, sure, Dr. Saju.
Yeah, that's a great presentation. I really enjoyed with your workflows. You take us to different workflows and finally you predicted. So one of my question, in your regression models, you showed various models, and I would like to know what is the agreement between the models when you see in that particular data sets. And the question follows, is it the same way you can see if you take another data sets?
Okay, okay, Dr. Saju, thank you for your question. It's a really interesting question. So if we see here, so back to our slide here, we see the different models, different classification models here.
Yep.
So the classifiers here.
Yeah.
So we can actually from this data, we can decide which model is the best for our data here. So if we see here the SVM model compared to linear SVM, or for example, we take here the random forest, the SVM behaves more polynomially. So if we have a more polynomial data, we use the SVM. So before actually we can compare which method is the best by printing out the matrix, the RMSE or the R squared. But we have to know before, we have to do the exploratory data analysis to identify the distributions and the correlations between features and features. And then from these distributions, we decide first which model is the best or the most appropriate model for our data. If we have a more linear looking data, so maybe we have like a pretty linear model, we have the just decision tree and random forest, it's enough. But if we use the SVM for this model, it can work really well, but it is not so suitable for this data that has only linear relationship. And if we have a complex relationship within several data, so if we see the in EDA before, we have lots of distributions. If we see that this data is complex in distributions or clustering, or it has certain clusters here, we can use the SVM for our model. And also, if we decide is this model can be applied in general for general applications, whether this model can be applied in our, for example, we would like to bring a model for field A or basin A to another basin, for example, basin B. We have to take care, because not all model can apply with different places. We have several distributions, so that's why I stress out the importance of doing the feature engineering, because we can make we can make a new feature that can capture the XYZ spatial distributions in our data. And then from this X, Y, and Z constraint, we can apply this model to another location. So I would like to say that spatial constraints are really important when we do the machine learning, because it decides whether this field it can be applicable to another field. And also before we are deciding whether this model can be applied, we can also correlate the data from the field A and field B. If this data is we can say that this is correlated, so we can apply this model. But if we don't have any correlation between field A and field B, for example, the DT, we have done enough correlation, we cannot use the model for field B. So we have ideally we have different models for different basins. So model for North Sea and model for Gulf of Mexico. So we have lots of model for specific for the basins. So that's my answer.
Oh, thank you very much. That's a very good detail information with respect to different data sets with the different regression models. Thank you.
Actually, right now I'm still experimenting with a model that can. So actually, this is the fourth data, and we know that North Sea are quite open data set, and I would like to experiment. So maybe in the next few months, this is my plan. This is my plan to make a model for the North Sea, because actually last week or last 2 weeks, the Equinor opened an open competition for prediction of phases, and from this result, we can use this model to apply to some wells in the North Sea that doesn't have any data. So this is the importance of collaboration. For this basin, we make one model, one universal model for one basin, and then for this model we can apply for certain field or certain well that has missing data. So this is really promising ways of thinking when we are dealing with missing data.
Yeah. Thanks, Johannes. I think we are up on time, but it was a very good presentation, good discussion on questions. So really thank you. And we can see you're really passionate with data analysis. That's very nice.
Thank you.
So with that, we conclude with this session, and next session is the valedictory session, so now I hand it over back to Christ College for the next proceedings. Over to you, Christ College.
Thank you, sir. So now we are moving on to our valedictory session. Let me now invite Dr. Nandini CV, Assistant Professor, Department of Geology and Environmental Science, Christ College Autonomous, for the welcome address. Over to you, ma'am. Sir, ladies and gentlemen, a very warm good evening to all. As per GMT, now it is morning time, so a very warm good morning as well. Today, we are at the end of International Geoscience Colloquium, which started on 10th November 2020. Past days, we had cutting-edge research presentations and discussions on various recent approaches in geosciences. Such international colloquium will bring social and educational benefits to both attendees and speakers. This colloquium succeeded in bringing together people from all over the globe. The colloquium was attended by speakers from over 14 countries, representing 29 well-recognized institutions with an average of about 200 participants from different parts of the world through Zoom and YouTube Live. This international colloquium was a great platform for participants and speakers to refine their ideas and for a high-level debate. This event was a place to meet and exchange or develop new critical ideas and approaches for the researchers in geoscience. A pessimist complains about the wind, an optimist tries to change it, and a leader adjusts sails. The sails for this particular International Geoscience Colloquium were adjusted by a person who is not only a great motivation to all of us, but a great visionary and a person who gave us the belief of bringing together this event. He is none other than our beloved Principal, Reverend Father Dr. Jolly Andrews, CMI, who is presiding the function. I welcome you, sir.
Next, I would like to welcome Professor Ashok Kumar Singhvi, Vice President, International Science Academy. Professor Ashok Kumar Singhvi is a renowned scientist in the field of quaternary climate and geochronology, radiation effects, and dosimetry. He pioneered the luminescence dating of desert sands and provided an understanding of the time evolution of deserts across the world. He is also enthusiastic in disseminating science learning to the common audience and also to the less privileged one in his capacity as the Vice President of International Science Academy. I welcome you, sir. Our IQAC coordinator, Dr. Robinson Punminisheri, his immense support and wholehearted suggestions were always a backbone to this colloquium. Welcome you, sir. The International Geoscience Colloquium had three distinct sessions. The sessions were chaired and co-hosted by eminent personalities like Dr. Angela, University of Exeter, UK, Dr. Sajin Kumar KS, University of Kerala, Adjunct Professor, Michigan Technology University, USC. Dr. Saju Menachiri, Geoscience Consultant, Georeservoir Solutions, Perth, Australia. Dr. Vetrimurugan Elumalai, University of Zululand, South Africa. Mr. Sak John, Geomechanics Team Leader, Schlumberger, Australia. And Dr. Lindo Alapat, Assistant Professor and Head, Department of Geology and Environment Science, Christ College. Also, he is the convener of International Geoscience Colloquium. I am honored to welcome the other speakers of the colloquium from various sessions, vice principals of Christ College, participants from different institutions all around the world, my dear colleagues and faculty members of Geology and Environment Science Department. Welcome you all. On behalf of Christ College Autonomous Irinjalkuda, we are delighted to offer a gracious welcome to all of you. Thank you. Welcome you all once again.
Thank you, ma'am. Let me invite Reverend Father Dr. Jolie Andrews, Principal, Christ College Autonomous, for the presidential address. Over to you, Father.
Uh, Hello, I think you can.
Yes,
Hello,
Father.
good evening. I think you can. Yeah, you can hear and see me.
Yes, Father.
Thank you so much. Professor Ashok Kumar Singhvi, the Vice President of Indian National Science Academy. Dr. Robinson, the IQAC Coordinator. Dr. Lindo, the convener of the colloquium of this International Geoscience Colloquium. The honorable members who have presented the papers from the different parts of the world. We are today Mr. Johannes from Indonesia, Dr. Muhammad, the data scientist from USA, Mr. Zakaria John from a geomechanist, a team leader from Australia, Dr. Simon Lang from University of Western Australia, Dr. Stephen from the United States, and our own Dr. Saju Menacheri from Australia, one of our prestigious alumni. Respected faculty members of the Department of Geology and the Environmental Science, research scholars, and my dear friends. At the very outset, I would like to specially congratulate and appreciate the Department of Geology and the Environmental Science for coming forward with this wonderful International Geoscience Colloquium. I like to express and say that this was truly, truly of an international character, having the renowned scientists and renowned academicians from the different parts of the world who contributed immensely. And we have here Dr. Um, Dr. Singhvi, the Vice President of Indian National Science Academy. And Ashok Singhvi has got a wonderful association with our Christ College. We especially appreciate the honorable presence of Dr. Singvi in our midst. And I would like to make a very few important aspects which we want to say here by seeing the immense potentiality of the geology. The Christ College management has this year has taken up and has selected the integrated geology, the 5-year integrated geology course here in the Christ College. And I'm happy to note that the geology already has got an alumni association that has strengthened here. I very much appreciate that aspect of strengthening in a very, very particular manner. We have also got a wonderful international association where the Department of Geology has spearheaded. The Christ College has already signed the memorandum of understanding with the Zululand University, South Africa, the University of Exeter. We are having association here in this Geoscience Colloquium, and also with the University of Kerala, we have got association, and Ministry of the Earth Science is also associated. We thank all these universities and especially the Ministry of the Earth Science for the association for conducting this Geoscience Colloquium. And we are also thinking about, and we have already have in our mind a faculty visiting scheme whereby our students can benefit from the faculty interaction, the interaction of the faculty from the different parts of the world coming over to the Christ College, and we are eagerly looking forward to this program. The Christ College, as you know, was established in the year 1956 and has been open to the students of all sections of the society, irrespective of the caste, creed, and religion and gender. Colleges at present 4,000 students, perhaps the largest number of the student community. Enrollment ratio has been concerned, enrollment has been concerned as far as the state of the Kerala has been concerned. We have got also the social commitment aspect of our institution in a very special way during this COVID-19 pandemic. We were able to distribute more than around 100 mobiles, especially due to the contribution of NSS and due to the contribution of the Tavanish, a social charitable association of the Christ College, which took the initiative in order to distribute these mobiles to the weaker sections of the society, especially to our students and to the nearby students. And we also had this association uh, taken level to a higher level where we had a 1 week program of Savishkara, which was primarily concerned for the differently abled students of this nearby locality of the three districts of Kerala. And we were very fortunate to have our Ashok Singhvi sir in the national level faculty development program, which we had here, which we took initiative here in the Christ College in collaboration with the GARD TLC, the HRDC ministry, and we also take this as a very wonderful privilege. So once again, I especially appreciate the Department of Geology of coming forward with this wonderful colloquium. My special appreciation to the colloquium convener, Dr. Lindu Alapan, and all the faculty members of the Department of Geology and the Environmental Science for this international colloquium. Have a wonderful time. Thank you very much. Thank you. May I remain.
Thank you, Father. With all due respect, let me invite Professor Ashok Kumar Singhvi, Vice President, Indian National Science Academy, for the valedictory message. Over to you, sir.
Thank you, Dr. Charlie Anderson, Dr. Robinson, Dr. Linto Alapat, all colleagues attending this conference. Last night when Dr. Alapat called me, I couldn't say no to him because I had a very pleasant association with Christ College. And now I've been interacting with Christ College so frequently that I would think I am a part of your faculty. So it was worthwhile, and I think you have been organizing great programs, including the International Geoscience Conclave. My compliments to you all, especially your Department of Geology. I was truly impressed to see that you had faculty and participants from 10 countries. And that's truly remarkable for a college to aspire to do that. So my compliments again. I noticed that you had talks on climate change, you had talks on geohazards, you talked on stratigraphy and sedimentology, and you had some talks on big data analytics. These are all very contemporary subjects, and I'm sure the participants would have learned a lot and would have taken back home. The question now is, what is it? What next? This is a question that we participants would like to think about it. Firstly, I'm sure they will transmit some of the excitements of what they've learned here back to their classes. And I'm sure that will be a value addition to the students' teaching program. I also believe that every teacher at whatever level, be it school, be it college, be it a university, has to be engaged in some kind of research program to be contemporary, to be at par with anybody else. Only then they can be effective teachers. So such meetings are helpful in keeping people updated, but we can do a bit more, and I'll come to that in a minute. We have often heard that there are lack of facilities for research in the institutions. But I feel that the research is done in the mind and not with instruments or facilities. So there are many opportunities which are available to all of you today in the country. And I like to mention those for your benefit so that you can really be doing research at the front rank without having to worry about the facilities part of it. As long as you have good ideas, I think much can be done. For example, if you look around your own area of living areas, if you look around the subsurface stratigraphy by looking at the trenches dug for housing, you can create a GIS framework for the subsurface architecture of the town in terms of stratigraphy. And this could be useful for all developmental work, be it sewage, be it housing, be it seismic microzonation. This will be a critical work. And this can be done on a weekend, going on a scooter or a car and looking at the stratigraphy and using GIS platform, which you have been taught in this. And this could be a very useful social work, and it will give you many new ideas on why certain phases were developed or not developed, why they got removed. So you can talk in terms of processes without having to have any research material with you or the instruments with you. Then we have just established, with the help of Ministry of Earth Sciences, National Center for Geochronology and other analysis. So one can go there, and if you have a good idea, you can do all possible measurements in geosciences, right from elemental concentrations to isotopic methods. Anything you want under the sky is available to you, free of cost. They will also pay you travel and stay if needed. So I think you should use this facility, and this facility is meant for people in colleges, in universities who do not have access to facilities. Then there are schemes of CSIR which funds you for smaller projects, idea projects. And I think that has not been used effectively. And I think I urge all of you to think of small projects around your town, around your place, which will give you a student's stipend or whatever. And then you can really develop new paradigms. The fourth possibility is that the academies, the Indian academies, have a summer training for summer fellowship program, which allows you to go and interact with anybody in the country you like to work with for 2 months. They take care of the airfare and the stay, and you could then build up a collaboration with them. So you should have ideas, and then there are many possibilities for you to take whatever you've learned forward in a meaningful manner. I think another important thing which has not been done in the country today is that a large volume of data has been generated on monsoons, on seismicity, on this. But I don't think it has been synthesized as rigorously as it could be. So sitting on your laptop with a few statistical techniques and few, of course, ideas, I think you can generate a lot of new products which could be of use to science and to applications both. I'll come to it, but I think it's important. Like, for example, we have monsoon. We know the monsoon has a spatial gradient. It may rain somewhere heavily, it may have drought somewhere. And these are dependent on various 10 parameters that they use in modeling. Now, have those 10 parameters remained so? Have the spatial gradients have remained so same during the past is not known. Large volume of data has been collected. Somebody needs to sit down and synthesize in a dispassionate manner whether monsoon spatial distribution timings have changed through time. And that will be a very important work to be done. I think there are many opportunities that people at your level could be doing, because you may not have resources, but you have a computer and you have a mind. And a lot of new good science. And once you do that, you will realize that you will get many more new ideas into your teaching as well. So I will urge you, all of you, to think seriously of issues around your house, around your college, around your institution, along your town, and see what new can be done. And there's lots of new potentials out there. Second thing I wanted to address to you was to tell you that we need to also put a value on our science. Most of us do science without thinking the value of our science. And that's what I mean is, you could have a section, you could have an ages on that, you could have a sedimentology done, you could do isotopes, you could do whatever. And then you can also write a very nice paper. But then if you analyze what value that paper has, in terms of either advancing the conceptual space or providing a product to society for use, I don't think we have taken that transit. So I think we all need to make that extra journey. And all of you who are probably may not have access to labs can do that journey by taking whatever has been published and see, can we use that published material to create products either in this conceptual space or in an application space. And I think a lot of new work can be done without the need of resources. And I will urge you to think harder, because it's most of the research and breakthroughs are in the mind. And I think we are not milking out the data that we have in effective manner. So we need to apply a kind of a filter on what is the value of our science. And I think that's an important part, because many times people ask you to make a statement of relevance statement. Relevance statement is that if you can tell your mother or a father or a layman, what is the relevance of your science? If you can explain them, then you will automatically get 10 more ideas, because bringing to your science to that level would imply that you understand the implications of your science very well. And I think that role can be played by this group, which has now been exposed to the state of art science, to develop new paradigms in doing it. Now, if you look at the other thing which you could be looking at is in looking at the conceptual space of thinking experiments. Now, COVID-19 is a good example that we knew that a pandemic of this kind can occur. We had in the past MERS and other viruses of similar kind, but still we were unprepared to have this virus. And today the whole world is in quandary. Just because we were not prepared, we were not thinking far enough. Similarly, climate change will be another area which will in near time will require so much of geological input that we will not be able to handle that. For example, you have floods. What is the geomorphic space of a river needed for it to function? 1 in 100-year time scale or 1 in 1,000-year time scale. You could work out and then tell these are the areas you cannot build. If you make that prescription, it's an enormous societal value, because it may save millions of dollars. Now, for example, Chennai airport apparently was built on a floodplain. Now, that if somebody has taken care of, wouldn't have billions of dollars could have been avoided. The expenditure to recover from that. So I think if you look around, there are a lot of enormous possibilities to do that. And like COVID-19, you can do a Gedanken experiment of climate change. What happens if the sea level increases? How the urban floods will increase, how the nuisance floods will increase. Could be a lot of new possibilities that you can do thinking experiments, build up scenario. And I think synthesis and building scenarios under eventualities of earthquakes, floods, or whatever hazards has never been worked out. And I think this is an important area of research which you can apply in your town. If there is a flood, what will happen? If there is an earthquake, what will happen? I think lots of new possibilities exist. The next point is the science outreach and science education. Now, geology is a complex science. And what we have done and we have learned over the years is that a global forcing in geology is translated to a local local effect determined by the local conditions. So the same climate change, same warming would be manifesting itself at various spatial and temporal scales. It need not be inter. Now, can we figure that out? And we need to do that. Otherwise, we'll be caught as unawares as we have been caught in pandemic. And people will curse us that we have not done our job properly. So can we build those scenarios? What if, suppose there's a flooding, what will be the manner of flooding? How can I actually take the people out? What will be the mechanism of evacuation? Can we create those scenarios? Strategies can be created. And these are straightforward applications of science, which has to be done, which has not been done. We need to be looking at those aspects carefully. For example, we know that the landscapes, same like my own work indicates to me that deserts, for example, responds to the same global climate forcing of, say, ice age at time scales from 100 years to 1,000 years to 10,000 years. So can we build in our management practices in the landscape land use planning that, and these kind of experiments, which are thought experiments, can be done on a laptop, and a lot of new data could be generated, which is of use to society. So that journey from local forcing and from a global forcing to local response has to be taken using all the data that is needed. And I think all the data that is needed is available because people have measured it, but not synthesized it. So I urge all of you to think of entering into a game of synthesis, of modeling, simulation on a simple terms. And there are lots of possibilities exist. And I think that will be a great thing, a win-win from this colloquium to take home with. And once you bring home this excitement to your classroom, then the students would be trained to look for future applied geosciences, which is the need of the hour. So you need to create students for the future. Finally, I think important to realize that although we have the luxury of the webinar or this, 90% of the country is not connected with internet and 50% students are not connected. We have to be conscious about the fact that we're already creating a class system because of those who have internet or not internet. So internet Brahmins and non-internet poor people. This is happening. And I think we have to be conscious and create modules that would ensure that those who cannot reach us through internet, we can reach them by some means. And I think all your lectures could be recorded or played or whatever, video clips or whatever you can do, please do that. Or maybe each one of you, for example, you have about 200 people on the screen. If you taught 10 people around you, around your housing colony, you taught 2,000. And if you have teach 10 people, or your students included, 100 students each of you, you're not now looking at 200,000 people being trained to understand the implications of climate change science? And what is the cautions, the precautions we need to take as a community? I think there's a lot of good work can be done without any resources, without any much, whatever we have, provided we think hard enough. We need not worry about what we do not have in terms of facilities, but we can still do a great science. Sitting at home on a computer with the internet, lots of new science can be done. And you have met with the experts in statistics to sedimentology to climate change, and you can really discuss and ideas and then come up with solutions which are useful to society. And I cannot say anything more than that, that geoscience will be the key science in the next decade, because global change is going to take over. Pandemic, we'll probably forget in a 2 years' time, but climate change will increasingly hurt us more. And it is our role to prepare the society for the future. A politician has a shelf life of 5 years. A bureaucrat has a shelf life of 2 years. So they look only for short-term solutions for their survival, but only an educationist, an academician, a teacher will have a shelf life and a vision for a lifetime. We cannot neglect our role in the society. We have to assume responsibility in the society and deliver good science, good education, good outreach, so that the future is safe. We cannot forget that part of it. So kindly assume responsibility, and only then our society will respect us as they should. Thank you so much. And I wish you all good time and good success in whatever you do.
Thank you so much, sir, for your enlightening words. Let me now invite Dr. Robinson Padmanasheri, Coordinator, IQAC, Christ College Autonomous, for the felicitation. Over to you, sir.
Thank you, Asha. Am I audible to you?
Yes, sir.
Respected Vice President of Indian National Academy, Professor Ashok Kumar Singhvi, Principal of College, Father Jolly Andrews, the convener of this colloquium, Dr. Lindu Alapat, and dear participants. It gives me great pleasure to be present here in the valedictory session of the International Geosciences Colloquium, jointly organized by Christ College, University of Kerala, University of Exeter, and University of Zululand. In this era of global climatic change, it's time for us to think more about our Mother Earth. Geology is such a fantastic subject which has direct relationship with conservation of our environment. Personally, I feel more collaborative studies are required with other disciplines like physics, climatology, chemistry, data science, etc. for the advancement of geology and also understanding the earth sciences. I extend my best wishes to all those who presented their research findings, who actively participated in the discussions and who contributed very well. May the deliberations happened during the colloquium lead more light into the intricacies of climate change and also the disaster management, which is very prevalent during this time. I wish all the success to all the participants and the organizers. Thank you.
Thank you, sir. Now we will have a session review or evaluation by the session chairs. Let me invite Dr. Sajin Kumar KS, Assistant Professor, University of Kerala, Adjunct Assistant Professor, Michigan Technological University, USA, for a very short review of our second session, Geohazards Mitigation and Management. Over to you, sir.
Thank you, Asha, for inviting me. I think I am audible, Asha?
Yes, sir, you are audible.
But I couldn't on my video, maybe it was disabled. Okay, no worries. Respected Principal Father, Singhvi Saab, other respectable persons who are attending this one. Yes, sir. First of all, I appreciate Dr. Lindo and his team for organizing such a long words and colloquium. Maybe it crossed the limits of International Geological Congress also. So not in the number of participants or something else, but on the number of days. And that too in the COVID days, bringing all the participants across the globe in a single platform. That is not a simple task. Rather, it required a Herculean task. So after my session, I have asked Dr. Lindo whether it can be done once in a year or once in at least 2 years. Though he nodded the head, I know it is a tough task, but I think in this colloquium, about 4 organizations have joined hands. I think you can give the responsibility one over the other in the coming years, so that you can also be a little free from this one. So you please think about it. I'm sure that I will join my hands with you for taking the responsibility in the coming years. And sorry, I couldn't bring all the participants or the speakers who have attended my session due to the shortage of time, because maybe when I send the mail, they are sleeping and they might not have waked up from their wards and blankets. So anyhow, I should, before I'm not taking much time, but I will substantiate what Singhvi Saab said one thing, because I have a second specialization on meteoritic impact craters. So Singhvi Saab told one thing. You see, being a developed country and being a state university or a college, we have limited access to the resources, or rather we don't have the money to do the work. But I can say an example. AMD, Atomic Minerals Division, have done a few drill holes in a place called Dala in Madhya Pradesh. Actually, their intention is to study atomic minerals. But fortunately or unfortunately, that area forms a meteoritic impact crater that has formed about 2.2 giga-annum. So what we've done is that there is a published borehole data. We collected that published borehole data. With that borehole data, we were able to identify the subsurface morphology of the impact crater by GIS methods. So the AMD people never come to know that their borehole data will be used in such a fashion that rather than their appreciation of their work, what we have done have got much appreciation, because everyone knows that only we have 200 impact craters on Earth. So I also request the student community who are here can utilize even the published data to bring the science out from that to the society. And saying about the natural hazard session, thank you very much for giving an opportunity to chair the section. I was able to bring 8 speakers, all prominent in the field of landslides and other natural hazards to bring, and on an average about 80 to 90 people have directly attended through Zoom. So that itself is a manifestation of how much importance natural hazards have to the society. So I'm not taking not that much time, because Dr. Lindo has a lot of things to be said in the coming time. So thank you very much once again. Thank you all.
Thank you, sir. Now let me invite Dr. Saju Menacheri to give a session review on our ongoing session. Over to you, sir.
Hello.
Thank you, Asha. Respected Principal, Christ College, Father Jolie Andrews, Professor Ashok Singhvi, and Dr. Robinson, and all other respected dignitaries on the valedictory session, and everyone present in the International Geoscience Colloquium online conference. Thanks to all the organizing committee for putting together international conference. We had different sessions, and I was on the session chair with my few colleagues, Zach John, Lindo, on developments in stratigraphy and sedimentology, big data analytics and artificial intelligence in geosciences, geoscience, and integrated reservoir modeling. So with all these different sessions, what we come to know to the latest technology and the latest understanding of the science, integrating each other, especially if you are looking to the big data analytics, it's integrating with all other parts of or disciplines of geology and consider everything into their papers or their talks. And this is one of the rare occasions to get the students, especially graduates to postgraduate to research students, as well as the young professional, to get an opportunity to see everything in the latest technology level and to understand and to learn a bit more on this latest technology. And also, as I know from Linda Alupad, these are all being recorded and being again, we can play back and to look in different workflows, technology, and look into these talks and presentation. Moreover, it's easy to contact all these presenters or the speakers and to get connected and to look into the future for new projects, as well as to learn a bit more from these people. So I'm not taking much time. It was a very appreciating International Geoscience Colloquium. We've been from November 10th to 2nd of December. So all the talks been very much appreciated with the well received with the attendees. So once again, thank you very much for the organizers and from Christ College and Kerala University and other two universities from Zululand, etc. Thank you for organizing all of these things. So that so now I'm handovering to Christ College for the next proceedings.
Thank you, sir. Now let me invite Dr. Vetrimurugan Elumalai for the session review. Over to you, sir.
Thank you so much, Asha. Good evening to everyone, and particularly the chief guest and our colleagues. I would like to express my thanks to the organizer of this colloquium, Dr. Lincho Alapat, who is a good friend of me since 2004. Really, I will appreciate and his effort. Another, also his team members, who is a part of this colloquium, those who have participated and organized this such a wonderful international colloquium. Really, it's a big challenge to organizing. I got so many experience before. But Inizulu and Christ College had a good relationship and maintaining this relationship since 2017. Based on that relationship, we signed the MOU with the Christ College, I think last year. The Christ College principals and my Vice Chancellor of the University of Zululand has had a discussion about the future collaboration and how to carry forward another 3 more years. So based on that, we plan so many projects, upcoming projects, and student exchange proposal also is possible for another few more years. So from this colloquiums, I discussed with a few of my colleagues and students. I think more than 100 students participated through from the South Africa. They're highly commended about these programs. They got a lot of knowledge and innovative ideas for. So, dear colleagues, really I'll appreciate you all once again. Who was Miss Ali from Canada. He was excellent presentation and elaborate resource hydrogeological issues of the Albertian areas. For collaboration with the Christ College in here.
Okay, I think he's facing some network issue. Okay, we know that a number of participants are attending the program through Zoom and YouTube Live. Your suggestions and feedback is very valuable to us. But
Can
due
you
to
hear
the
me?
yes, sir. Yes, sir. Okay, so your suggestions and comments are very valuable to us, but due to the time constraint, I request every participant to kindly post your feedback in the chat box. We will definitely go through it. Now let me invite Dr. Lindo Alapart, Head of the Department of Geology and Environmental Science, Christ College Autonomous, also the convener of the colloquium, to extend the vote of thanks. Over to you, sir.
Unmute yourself, Linto.
Linto, you're on mute. So
sorry about it. Thank you, Asha, and greetings of the day and good afternoon, everyone in India. The Geoscience Colloquium that was jointly organized by Christ College, University of Kerala, University of Exeter, and University of Zululand, which was supported by Ministry of Earth Science, Government of India, is ending today. It is indeed a happy moment for all of us with a successful near completion of the 7-day-long deliberations on various themes of geoscience. For the convenience, it was brought into the framework of 3 major themes, which includes new proxies of climate change of the past and present, geohazards, mitigation and management, developments in stratigraphy and sedimentology, big data analytics, and artificial intelligence in geoscience, geoscience and integrated reservoir modeling. We had about 29 speakers from 14 different countries and representing 29 institutions across the world presenting their work. We had Professor Jyotiranjan Ray, the Director of National Center for Earth Science Studies, Kerala, India, representing the Ministry of Earth Science for inaugurating the function. The aim of this colloquium was to overcome the barrier created by travel ban due to the COVID-19 pandemic and the vacuum created in the teaching learning space for both the researchers and students. Now, let me go into my duty of expressing our gratitude to all gathered here and worked with us in the past few days to make the program a success. Let me thank Professor A.K. Singhvi, Vice President, Indian National Science Academy, for his enlightening valedictory message today about future directions and opportunities of geoscience education and research in general, in India and also globally. Thank you, sir. Join with us for today's closing ceremony of this event. Though it was a short notice, I thank you for your continuous association and support with us. I thank the manager of Christ College, Dr. Father Jacob Nyiranjambili, who was always giving his support in spreading the spirit of knowledge to a wider student community. Thank you, Father. I also would like to thank Christ College Principal, Dr. Jolie Andrews, whose continuous and unconditional support to the progress of the department, both in terms of quality and quantity, which has made this program possible these days. Thank you, Dr. Jolie.
thank you.
Let me also thank Dr. Robinson P., the IQAC coordinator, and his team who stood with us in doing pre-colloquium preparations and getting necessary help when required. Thank you, sir, for your help. It's also important to express our gratitude to the session chairs and speakers. I would like to thank Dr. Angela Galileo Sala, University of Exeter, UK, who was also co-chair of the session, New Proxies of Climate Change, and worked hard in making the program a reality. Thank you, Dr. Angela. Dr. Sajin Kumar KS, University of Kerala, and Adjunct Assistant Professor, Michigan State University, Michigan Technological University of United States, who has accepted our request to co-organize and chair the session on geohazards. Our heartfelt gratitude goes to you, Dr. Sajin, for your effort in making the session very interesting. Dr. Saju Manacheri, Georeservoir Solutions, Perth, Australia, is an alumnus of our department and has agreed to co-organize and chair the session on developments in stratigraphy and sedimentology, big data analysis, and artificial intelligence in geoscience, and integrated reservoir modeling. Thank you, Dr. Saju, for making the session very interactive and also giving an interesting talk on carbon dioxide sequestration in geological formations. That was very well received. Next, let me thank my good friend, Dr. Ermalai Vetrimirugan from University of Zululand, South Africa, for helping us with jointly organizing the program and chairing a session on geohydrology. Mr. Zach John, geomechanics team leader, Schlumberger, Australia, was the co-chair of the last session and will also be giving a talk after this program. Thank you, Zach, for your valuable help in these terms. Now let me thank various speakers of 7-day-long sessions. I'm aware that the list is long, but it's important to mention their dedication to make the session possible. In the session 1, new proxies of climate change of the past and present, we had Dr. Brian M. Chase, Director of Research, CNRS, France, and Vice President of International Union of Quaternary Research, INQUA. We had Dr. David Naff, School of Chemistry, University of Bristol, Dr. Tom Sims, University of Leeds, Dr. Rabiul Biswas, University of Lausanne, Switzerland, Dr. Annie Alexander, Director of Research, CNRS, Dr. Sakawan Chuanchai, University of Bangkok, Dr. Runa Anthony, National Center for Polar and Ocean Research, Goa, India, Dr. Dylan Young, Department of Geography, University of Leeds, UK, Dr. Nicole Sanderson, University of Montreal, Canada, representing the first session. And we have speakers in the second session, Geohazards Mitigation and Management, which was the inaugural address was given by Dr. Shekhar Lukos Kuriakos, Member Secretary, Kerala State Disaster Management Authority, Government of Kerala. After that, we had lectures from Professor Brian G. McAdoo, Yale National University College, Singapore, Professor Thomas Uman, Michigan Technological University, USA, Professor Cees van Westen, University of Twente, the Netherlands, Dr. Tabas Ranjan Martha, National Remote Sensing Center, Hyderabad, India, Dr. Karen Rieux, United Nations Environmental Program, Geneva, Switzerland, Mr. Vishnu CL, Michigan Technological University, USA. And representing the third session, developments in stratigraphy and sedimentology, big data analysis, and artificial intelligence in geoscience, and integrated reservoir modeling. We had Dr. Mohammed Al Khalifa, Senior Geological Consultant, Saudi Arabia, Dr. Kevin Jarvis, Geophysical Consultant, Perth, Australia, Dr. Mahood S. Nasga, Senior Geological Consultant, Saudi Arabia, Ms. Lali Anil, Hydrogeologist, Environmental Site Assessment and Remediation, Calgary, Canada, Professor Mbata, Senior Lecturer, University of Zululand, South Africa, Professor Hector A. Orengo from the Landscape Archaeology Research Group, Catalan Institute of Classical Archaeology, Spain. Today, Mr. Johannes Nuara, the reservoir geophysicist, Jakarta, Indonesia, and followed by, we will have 3 more sessions by Mr. Zach John, that is, he is from Geomechanics team leader from Schlumberger, Australia, Dr. Simon Land, Professor School of Earth and Earth Sciences, the University of Western Australia, Professor Dr. Stephen Hasiotis, Geology Professor from University of Kansas, USA. Our sincere gratitude goes to all of you, all of these speakers who had spared their time. Many of the time, it was like early in the morning, and for example, in USA and Canada, or late in the night, they spare their time to attend the program. Thank you once again. Now, I would like to thank all the participants across India and also from abroad who took time out of their busy schedule, excuse me, and have come online here to attend the program. Without their active participation, the program will not be a success. Thank you all, dear participants. Now, I would like to thank my colleagues, each and everyone in the Department of Geology and Environmental Science who worked with me to make this event possible. The local organizing committee include Professor Dr. Tarun R, Anu J. Pannar, Ms. Roshni PP, Mr. Gopakumar PG, Roshni KS, Ms. Asha Marin Jolly, Dr. Devi, Dr. Nandini, Dr. Subin K. Jose, Dr. Manju NJ, and Dr. Rega VB, all of them assistant professors at Department of Geology and Environmental Science. To compensate for the timing across the world, we had the sessions arranged late in the evenings, as it will be today also. And I'm glad that all of them have stayed back in the college until the program is complete. Thank you, everyone. Special appreciation to Ms. Asha Maril Jodi and Dr. Nandini CV and Mr. Tarun, who coordinated the programs every day for the smooth conduct. I also would like to thank our IT team, especially Mr. Prajesh and Hariharan for the successful organization of the program online and also doing live stream in the YouTube live. Thank you once again for all help and cooperation that was rendered to me and to our team to make the program successful. With these words, may I conclude, and I request all the participants to stay back for the few more interesting lectures that happens followed by this today. Thank you, everyone.
Thank you, sir. Now that brings an end to our valedictory function. Now we will resume our ongoing session. Let me invite Dr. Saju Menacheri and Mr. Zach John to take over the session.
Thank you, Asha. So now the session continues with the geoscience and integrated reservoir modeling session. I would like to introduce the second speaker of today, Mr. Zachariah John, geomechanics team leader, Schlumberger, Australia. He will be presenting on the subject on applications of geomechanics in solving drilling and production related challenges in oil and gas fields. A few words for Zach John. He's a team leader for the geomechanics and acoustics groups in Schlumberger, Australia, based in Perth. He graduated in mechanical engineering from IIT Delhi in mechanical engineering. In Schlumberger, he was held a technical and management position in wireline and interpretation groups. His passion for geomechanics and its multidisciplinary requirement drew him into the field of geomechanics for last 10 years ago. He is currently involved in rock testing design, construction of 1 and 3D geomechanical models for addressing challenges related to wellbore stability during drilling, completion integrity, sanding, compaction subsidence, and the fault stability over the life of the field for oil and gas reservoirs and CO2 sequestration projects. He is a member of SPWLA and SPE and was the past president for the Formation Evaluation Society of Australia in 2010. When he has some free time, he enjoys gardening, vermiculture, cycling, also biblical theological studies and serving at his church. So now I'm welcome to Mr. Zach for his talk.
Thank you, Saju. You can hear Saju?
Yeah, we can.
Yep. Okay, very good. So we're going to go through, we have got about 40 minutes of time when I can walk you through geomechanics. And geomechanics is a fairly new area in the oil and gas industry. Things have been quite developed in the mineral industry where its formations are shallow, so you can get samples right out. You can conduct experiments right in the cavity or quarried area. But oil and gas industry, most of the stress measurements and rock characterizations are happening about 1 to 2 kilometers deep. So we rely a lot on measurements that are made from a lot of the logging tools and other sampling methods. So let me walk you through what happens in this area of geomechanics and how it solves many, many problems in the oil and gas industry. So first of all, why you have this issue of geotectonics or stresses build up in various different parts of the field. And you can see it's mainly due to plate tectonics. different parts of the world are squeezing and relaxing in some other areas. So for example, near Australia, going around New Zealand is this plate, and they're squeezing here, and therefore there is mountain building activity over here, subduction on the other side, and therefore quite a bit of disturbance is happening. So there's a stress field going around in the world, and therefore wherever you drill, there will be stress variations happening as a result of that. Not only that, when you start to withdraw fluids, then you're altering the stress again in the field. And if you want to drill again in that field after 5 years, things will be different. So all those complexities gave birth to the area of geomechanics. I would say around 1980s, 85s is when the area of geomechanics evolved in the oil and gas industry. So what are the challenges in the geomechanics area? So when you are drilling a well, this is the well. First of all, the selection of casing points based on geomechanical results is an area under geomechanics. There may be overpressured areas which we have to understand and predict. Also, when you drill wells, especially deviated wells, you could have wellbore instability issues because there is a big, what you call, enlargement of the hole. Rock keeps falling and can jam the drill pipe or the BHA. Each of the BHA or bottom hole assembly with drill pipe and sensors can be easily $1 to $2 million. So very expensive affair to lose there. You can have fluid loss, that you inadvertently fracture the formation and the mud losses happen. And as a result, the mud column height reduces and you can have a blowout. So very, very dangerous situation to have lost circulation. You want to understand to do hydraulic fracturing. And the key component of that is rock properties and the stress field. Both are answer solutions from geomechanics. And then completion integrity. As you complete a well, and you start to produce oil or gas, with it could come the sand or the formation. So will that happen or not? Would sand control be required or not? These are answers provided by geomechanics. All these solutions are at the wellbore, but we are looking at things far away from the wellbore. For example, as you remove the fluids, there will be compaction, squeezing of the formation. And further above, there can be subsidence. Subsidence as large as 5 to 10 meters can be there in certain situations. So very dangerous. If there's housing complexes above or a platform above, then they're going to be sinking. The Ecofisk field, as the whole platform subsided, took around $1 billion to raise that platform up back to its original position otherwise it would sink. So big ramification. Then fractured reservoirs. Whether sometimes you drill into these fractured reservoirs to draw the fluid out. Under that stress field conditions, those fractures may be very permeable and is conducive to fluid flow. But as you produce from the field, the stress direction could change, and these very good permeable fractures could start to close. So that prediction is under geomechanics. This is a slide, actual reality, where the proper evaluation was not done. And as fluid started to come out, so was the sand. And you can see all this sand is produced from the wellbore and is uncontrollable. Literally, that well is lost. And each of these wells could be very expensive to drill and complete. So that's all lost money. And sometimes even sand gets into the production facilities, choking the field, choking the completion gadgets. Here is another application where you have the field over here, a field which was producing, and they started to notice that around the periphery of this field, the casing started to shear. And therefore, that's they just lose that well. And they were wondering, what could it be? Is it corrosion? I remember doing logs in that field quite some time back and understand corrosion. But actually, as we understood further, it was as the field was compacting, is like a pack of cards. The formations start to slip over each other, and therefore they were shearing the casing at a very shallow depth, maybe 500 meters or so. So the solution was very simple once we understood it. Just over drill that area so that the formations don't touch the casing, and the problem was solved. So once you understand the reason, the solutions could be very simple. This is another field where let me just get the pointer. Yeah, where the the casing shear was happening again at the periphery, and therefore we are seeing again the issue of compaction affecting the formation slipping over the reservoir. So how do we address these problems? We go by constructing what we call the mechanical earth model, and there is 1D, 2D, and 3D. 1D stands for one dimensional along the depth. 2D stands for if the area is faulted and you want to see what is the impact over the other, what will happen there according to this trajectory of scene, you're going to consider a layer cake model and transfer the properties from one zone to the other. So then the next one would be 3D mechanical earth model, where you construct a finite element grid of the entire field and start to understand what will happen with changes happening either in properties, pressure, or tectonics. Very powerful modeling approach that's evolving. So let me give you a case study of the results from one of the geomechanics studies that were done. So this was a land well, tight gas, and they drilled the well, but they found that the caliper or the hole was very, very enlarged. When the hole is so much enlarged, then you can't acquire the geotechnical data or logs, what we call the density, gamma ray, neutron, very difficult to acquire because your borehole contact is not there. Not only that, once you case it, cement it, and perforate and do hydraulic fracturing, the entire evaluation was in question in this well because the cementing behind the casing was not good. So when they did hydraulic fracturing, the fracture went into some other zone, and the results they got were not representative of the zone. The whole well was a loss, $30 million of loss this customer suffered. So when you look at how we analyzed it, we constructed a geomechanical model utilizing drilling data, wireline logs, core information, borehole images that were required, constructed the model, and this is the result of that model. So let me walk you through what it gives. This is in PPG or mud weight density. So it will tell you that if you were to drill through this white space, somehow, all in this white space, you will have a gun barrel hole. But often that's not the way. You will weight up the mud for a particular density and just drill through. So in this particular case, when we analyzed, their mud weight was this black line. And you can see that as they went into the red zone, where they were grossly underweight in their mud, they suffered huge enlargement. Then they realized that, increased the mud weight, but that was not sufficient. And they realized that they were still having a lot of stuck pipe issues. Then they increased it further, and they came over here. Ideally, they should have been in the green zone. So if you were to drill this well again, we would partition the whole interval in depth under two zones, have a mud weight up to that point, then increase the mud to that level, and then drill this whole section. And then you would have acceptable well bore to record all the data. This is what they did in the second well. They grossly increased the mud weight based on our geomechanical model, and that well was a success. Great application of geomechanics. The next application is hydraulic fracturing, and a little bit of fundamentals of in hydraulic fracturing. These are three stress profiles I'm giving. So all the stress in the ground can be partitioned into three principal stress or translated: vertical stress, and 2 horizontal stress. So most of the time, so therefore we are plotting these 2 stresses, 3 stresses: vertical stress, horizontal maximum, horizontal minimum. In this stress field on the top, as we have shown, since the minimum horizontal stress is the least, you will get if you'll get a vertical hydraulic fracture. So this zone and this zone, where the minimum horizontal stress, which is the green line, is lower than the vertical stress, which is called normal fault regime, then you will get a vertical hydraulic fracture. If it is higher, these minimum horizontal stress is higher than the vertical stress, then as you stimulate the formation, you will get a pancake type of fracture. And often we do this hydraulic fracturing, or what we call hydraulic stimulation, to make rock connectivity in low permeable zones like shale gas or very tight gas formations. And you want a vertical fracture to go as deep as possible to create reservoir contact with the formation, so that you have a large surface area that can feed oil and gas back to the wellbore. So understanding the stress regime is important, because you want most of the time vertical fractures rather than the horizontal fractures. So very important for designing your hydraulic fracturing work. And the two important parameters that go from geomechanical model is the calibrated stress and the maximum horizontal stress direction, and some properties like Young's modulus. So how do this affect the hydraulic fracturing stimulation? If the minimum horizontal stress profile is of this nature, where there is a large contrast between the zone of interest, for example, this is a sand zone, and above and below is shale zone, then you get a very deep fracture. Whereas if it's very shallow contrast between the zone of interest and the bounding layers, then the frac tends to propagate into the shales and you won't get a deep fracture, very ineffective. And same way for Young's modulus. If the formation is very stiff, then the formation will not open up. And you want to open up fairly well, so that as soon as you open up, you can pack it with propens like sand. And therefore, once you stop pressurizing and release the pressure, the formation will not collapse, but will stick or keep open around the sand particles or propens. So to understand how big that aperture would be, Young's modulus is a very important output that again comes from a geomechanical model. So let's look at a case study of how hydraulic fracturing in shale gas was applied. So this is a horizontal well where there are a number of stages, stage 1 to stage 3. And one of the challenges always in shale gas was, how would you stage these perforations? So each stage has a number of perforations. So earlier on, as we were drilling shale gas wells around in many countries, we were just perforating and equispacing the stages. So just geometrically divide the entire length. But what we found was that as we did that, the production profile coming from this well, from these various perforations, was actually not the same. There were high increase amounts from certain areas and very low production from other areas where the perforations were there. So what is the reason for that? In fact, we found that 70% of the gas came from a few perforations, and a lot of perforations, of half of them, were not even producing. So it's a waste of money and a waste of a lot of energy in having unproductive zones. But as we looked at the stress profile, so you will see the look at the stress profile, wherever there is low stress, you could see that the perforations and production really gave good results. Whereas anywhere there was high stress, even though you perforated it, no production came from it. So there was a very good correlation between the stress and the production. And understanding the stress profile is a geomechanics area, and the paper was published as SPE 103202 that tried to predict what is the stresses And therefore, in future wells, what they started to do was target and create the stage in those low stress areas and avoid the high stress areas. And we found that 90 to 95% of the perforations were productive. So very huge competitive advantage and efficiency gains through doing geomechanical model. So we have seen the applications of this construction of the mechanical earth model. How do we go about constructing such models? So here is a cartoon. Because these formations are very deep, we have got inputs, very few, very important logs that we require. One is gamma ray, sonic log compressional, sonic shear, density, borehole images, forearm caliper, and mineralogy. So in the order of importance are these logs. The sonic is very important. It's like if you want to understand how strong I am, maybe you can just hold my muscles and you get a feel how much weight I can lift. Same is for the formation. By utilizing sonic compression and shear, you're vibrating the grains and understanding the properties of that. Geophysicists have been using that quite often. They have been using the compressional, the shear velocities, and the density to get what you call the dynamic Young's modulus, dynamic Poisson's ratio, which are geomechanical properties. And we call it dynamic because you're shaking or vibrating the grains of sand or formation using sonic signals. So you're vibrating it in situ. Then you have static properties like static Young's modulus, static Poisson's ratio, where you take the rock sample and in the laboratory, slowly squeeze it to find these geomechanical properties. But what is interesting is there is a relationship between the dynamic properties and the static properties. So what we do is, because you can obtain the sonic logs continuously in the wellbore against sand and shale facies, you can get a dynamic log. And by doing rock tests at a few sample points, I can get the static parameters. And then utilizing a transform which I developed based on a number of rock tests and correlations that you can see, I can get a static property log. And so for that, I can construct the friction angle and UCS. These are the four main geomechanical properties that we construct. We call the muscles of the rock, the muscles part on. And then we, utilizing what we call the poroelastic equation, we can then, using the Young's modulus, Poisson's ratio, pore pressure, Biot's coefficient, make a profile of the minimum horizontal stress. And we can calibrate that or shift my whole profile based on some measurements I would make during leak-off test or extended leak-off test while drilling the well, or what we call from MDT stress test, or what we call formation tester. So we straddle using two packers and we inflate in the middle. And as you inflate in the middle of the two packers, straddle in the hole against a formation, you can crack the rock. And from that cracking of the rock, you can get an estimate of stress. So that's done there. The vertical stress you just get by integrating the density all the way to the surface. So you have that. But the maximum horizontal stress, the red curve, you can't measure it. So what we do is we use an iterative process. Since you have drilled a well and you have put some mud weight there, if you are very low in mud weight, then you have breakouts or the borehole cavings start to come in. If you put too much of mud, then you crack the rock and you get tensile failures or hydraulic fractures. All those drilling induced failures can be seen on the borehole images. So what we do for that particular mud weight used, we run this model and see, does it give a hole enlargement? Do we predict that breakouts and tensile failures that we see in the images? If there is a match, then we know that our estimate of the poroelastic parameters are good, and we have a calibrated numerical representation of the earth properties and stress, what we call as the 1D mechanical earth model. So quite an involved process, and it took quite a few number of years of good data acquisition to understand all this as we apply civil engineering to about 2 to 3 kilometers downhole. And this is a table of some of the very, very important measurements that we have. So we have compressional, shear, density, images, leak-off tests, borehole images, well logs, drilling experiences, a 3D model of petrel, a static model, seismic inversion. All this is going to help. No wonder I like this area, because it pulls in your domain experience from geology, from geophysics, from logging, from petrophysics, and geomechanics. Everything gets together as we work out to find out about the earth. It's very much like a doctor looking at a patient, which is the earth, in terms of stresses and properties. So once you have made the geomechanical model, then you are able to get answer solutions for drilling in terms of wellbore stability, in terms of answers for hydraulic fracturing or sanding production, or in terms of the fault stability. All these things can be derived from this 1D mechanical earth model. So a lot of applications. But the future is not that. The future is going into the 3D realm. So initially, you had what we call the static model, or what we call the static geological model, where the geologist makes a numerical representation of the channel sands, the facies, of the topography. Everything is put into a numerical grid. And so it's very easy to quantify, like what is the volume of rock, porous rock? What is the volume of hydrocarbon? All that can be calculated from that static model. Then came the dynamic model, fluid model. So you have softwares like Eclipse, Intersect, and T-Navigator, number of software. Given the fluid and the fluid properties in the field in a gridded model, by drilling wells and having a certain flow rate, how much oil or gas can I produce during the life of the field? How many wells are required? In terms of oil and gas that is produced, how does it translate into money? All that is come from the dynamic reservoir model, where reservoir engineers are the domain experts in that area. But evolving very fast is the reservoir geomechanics model, where we pull in the static model and the dynamic model together to predict what is going to happen in the whole field in the life of the field. It's like a crystal ball. Literally, as companies are beginning to utilize this technology, they're able to predict what will happen down the line. Will a fault get activated, which we never thought, or a casing get sheared, which we never thought would happen, or the formation microstructure collapsing just because of too much stress? All that answers come from 3D model. So here is a representation of a field in 3D. Assume you have single 1D models in each of these wells. The problem is those 1D models, while they may be good in giving a brief idea about what may happen in that field and its vicinity, in that well and its vicinity, the 3D model honors the changing topography, the changing pressure regime in the life of the field, and therefore all those complexities of fractures and faults all can be taken in to understand the stress field in that whole model in space and in time. So all these problems like caprock integrity, if you're doing gas storage, how much gas can you go on pumping like in a balloon before the caprock might have integrity issues, cracks might develop? Or in terms of compaction subsidence, how much can the subsurface be subside? Or porosity permeability changes. If you deplete the formation too much, it's like eggshells. They'll all collapse at a certain time, and there will be pore structure change with permanent change in porosity. Fault reactivation, a huge application where we can now start to predict whether a certain fault can get reactivated, etc. So number of applications that come out of it. So how is a 3D mechanical earth model constructed? It's a very complex process, but great thing is that we are using now the backbone of the static model that is constructed and the dynamic model that is constructed, and utilizing the whole thing itself to construct the 3D model. So we make use of seismic inversion. We make use of the 1D mechanical earth model already done in the field at a few well locations. We look at logs and cores that go to calibrate the 1D model. Based on all that, from the original static model, we embed that. So it's like taking a piece of a formation there, a field, and putting around it sponge, so that when I numerically perturbate it, give disturbance to it, the stress very softly lands on the reservoir. So there is no numerical, what you call, aberration due to that. So we embed the model in step 2. And then we do property modeling, where the properties of Young's modulus, Poisson's ratio, UCS, friction angle, all that properties, geomechanical properties, we intelligently populate that into the whole 3D grid of the field. We could use seismic inversion or stochastic methods. Many methods are there. And then we find out the pore pressure in the entire field. And there are many methods to do that. And then we populate the entire model with the faults and fractures. And then we equilibrate that entire model and with the initial boundary conditions, so that all the cells will equilibrate in stress. And then we can do what we call one-way coupling or two-way coupling, because once you make that model, initial stress model, why would there be any changes of stress or issues in that field? It's purely because either you are removing some fluid or you are injecting some fluid. So because of those changes in the way you inject and withdraw the fluid, the stress variations can happen, and we can see those changes in the life of the field. Maybe 1 year, 2 years, 10 years to abandonment. And out of that come a number of answer products. So one is, which faults will become critical? Will that fault become critical as you deplete quite a bit? What about if you want to drill some intermediate, some wells in the field, in the midlife of the field? Because the fracture gradient has reduced, how much has it reduced? That's a very important question drillers ask, and we can have that. As we said, compaction subsidence, even completion integrity. So we make a finite grid around the casing and can predict whether there will be a cement collapse or casing collapse by these changes. And of course, which parts of the field is more prone for sanding. So all those solutions come up. So let me give you some examples of what came out from these 3D studies. So the very first one is a reservoir compaction with production. So here is a geomechanics prediction. So we went ahead to construct the model as we did, showing the methodology I presented before. And we saw that the compaction footprint is about, there'll be 1.4 meters of compaction. So you can see a representation of what we predict based on the 3D modeling in the grid. But what is interesting is, about 6 years later, they did a 4D seismic inversion and found that approximate compaction is about 1.5 meters. So pretty good prediction versus actual what we got from the field measurements. Very encouraging. The next is on fault stability. This was for a field in Australia itself, where they had various events. So in this particular case, this is a 3D grid we are showing, and there is a fault over here, which you are not seeing very well right now. The maximum horizontal stress is in this direction, roughly east-west. And the problem the operator had was, they were doing water injection, and normally you want to get a steady pressure, but suddenly the pressure dropped, which means somewhere in the field, a crack happened and the fluid is losing. And they did not know, they did not anticipate this. And that is very bad for the field, because now instead of the waterfront from water injection going and flooding the field, it is going through somewhere and escaping without giving increasing the waterfront pressure. So when we did a geomechanics model from the initial conditions, we stepped the model into about 3 or 4 years into the future, or that came into the present really from the earlier years. We could see what is happening. Because of that pressure regime, some areas depleting on the other side of the fault, this area injecting, this particular fault had become critical. When we say critical, means it is about to slip. And when you're about to slip, what happens is a pathway for the fluid is made and the fluids can go in. And that's exactly what happened. That baffled the asset people, because that fault was actually perpendicular to the maximum horizontal stress. So, you know, when a fault or a breakage is against the maximum horizontal stress, you only expect that fault to close. But it became critical because the way the pressure variation was happening in the field. So in a 1D sense, you could have never predicted that, but 3D really helps us to predict. And therefore, now that you know that the model works, you could utilize this in the management of the field in other parts of the field, that the same mishap doesn't happen. So you can use it as a tool to fast forward it to many years in front and see what might happen in another part of the field, for example. So we are coming to a close. We discussed many applications of geomechanics. We considered the 1D mechanical earth model, where we look at pressure, overpressure areas which geomechanics can predict. We looked at wellbore stability, how a 1D model, once it's constructed, will help us to understand whether what suitable mud weight should be required in a well we are going to drill. It'll help us to understand fracture gradients for loss circulation. We also will look at hydraulic fracturing. We looked at Young's modulus and stresses, which are important inputs to the hydraulic fracture simulator. We also looked at how in the sanding study it could be applied, and not only at the wellbore, but how it has applications for compaction subsidence, fault stability, fracture reservoir permeability changes, all through the 3D mechanical earth model, utilizing the static model and the dynamic model pressure variations. Marry them together, add to that the geomechanics component, and you have got a very good 3D geomechanical model, which you can step through time of your production forecast story to see the geomechanical story in the field. Very powerful. So with that, I come to a close. We have a bit of time, about 15 minutes, so I'm open to questions.
Thank you, Zach. That was a great talk regarding all the geomechanics applications in drilling. So I would like to ask the attendees or the audience to type any questions you have in the chat box, or you can unmute and ask the question directly to Zach. Before any question comes, I would like to ask one of the question, Zach. You know, the perforation versus fracturing, especially and unconventionals. What are the main or the major concerns that the drilling engineers has to look for?
Okay, very good, Saju. So if you're taking perforations, mainly it comes in the area of reservoir engineering or production engineering. They want to know that after you perforate, so perforation consists of having a steel casing, and then you have the formation behind that is oil and gas bearing, and then you shoot charges which make a hole through the casing and the cement, they will make about 2 to 3 feet of a hole about an inch size diameter to allow the reservoir fluids to come in. So the main challenge there is that you only want the fluids to come in. If the formations are not very competent, then along with the fluid comes the sand. And that's what you saw as the first few slides of the challenge. They never anticipated that sand to come, and then all that sand came in, choked the wellbore, lost well. So that's one of the challenge. So geomechanics answers that. We can, looking at the rock properties and constructing the model, we can predict that if you make a hole of a tunnel that small and there is the particle size of grain size variation in that reservoir, then with that drawdown, will sand also produce or not? That's an answer from the geomechanical field called sanding study. But the construction of the 1D model is the base. From that, we make this additional modeling we do. So if we know that it's going to sand, then the production engineer and the reservoir engineer can take some mitigation steps and put what you call sand control, similar to what you do for a well, for water well in your house. You drill a well and then you put a liner and you pack it around with sand, beach sand, so that particles from the well, all the dirt and clay will not come in. The sand will stop it. Same thing, that's called sand control. So they're able to do that. Or there is another very interesting area. If you have this whole zone which you need to perforate, maybe the top zone is more competent than the bottom zone. So instead of perforating all the interval, you may selectively perforate the top zone. So an operator in Russia, they were spending millions of dollars for sand control and losing productivity. They did the sanding study and realized, wow, we can only perforate the top zone. Yeah, production initially drops, but they don't have to do all this sand control completion strategy there. So that is that area for perforation. Then coming into hydraulic fracturing, one of the challenges in hydraulic fracturing is the operation takes care of taking fluid and pumping it at a particular rate and under some pressure. And those pressure and rate are operating parameters for the hydraulic fracturing engineer. And it's always a question, if I do it too fast, how will the frac behave? So while they can do those simulations using simulators, hydraulic fracturing simulators, the very important parameter in that is, as you saw, is the stress profile and the Young's modulus. Because if you get that wrong and your stress is such that your minimum horizontal stress is very close to the vertical stress, which was the case for actually coal seam gas projects in the north of Australia, where the stresses are very high, operators did not construct a 1D model and blindly started to just bulldoze the formation with a lot of fluid at fast rate. They would call it fracking the hell out of the formation. But they didn't realize, because of the stress regime, the hydraulic fracture would not go vertically to make a very good contact, but would go and change direction and become horizontal and would go horizontal. So after doing hydraulic fracturing for 4, 5, 6 wells, they said, hey, it's not producing at all to the amount of effort we put in for hydraulic fracturing. Our prediction was it should produce a lot. And that's when they started to analyze the stresses and do a geomechanical model. And they said, wow, the stresses are very high. And therefore, that changes the way I do hydraulic fracturing. Now I need to do what we call a pinpoint fracture. Push the fluid very carefully because I'm so close to the vertical stress that I grow the fracture slowly vertically and get the best out of it. So those are two ways, Saju, in perforation strategy and hydraulic fracturing, where geomechanical modeling helps in addressing the challenges with respect to the design of those completion strategies.
Yeah, thank you, Zach. That was a very detailed, very at the academic level of details on that answer. Thank you very much. There is a question in the chat box.
Oh,
How I can read for you.
yeah.
How we can predict overpressure areas in terms of geomechanics studies?
Oh, very good question. So, sorry. So the geomechanics study, so pore pressure can be there in two areas. One is in the sand area, the reservoir rock, and the other is in the shales. So the sand zones normally can be sandwiched. There are a few types of pressures that we talk about. One type of pressure is type 1, where a sand body very quickly got submerged and a lot of shale or clay particles went on top. And therefore, the pressure inside that sand could not equilibrate. And so is in the shale, cannot equilibrate. So this is called very rapid deposition. And normally we can find these zones by the signature of the sonic in the overbearing shale. So what we do is once we know that we have drilled into overpressure sand, we have recorded the sonic, we start to evaluate that sonic and see if that overpressure signature from the sonic. Whenever the shales are overpressured, as a result of which the sands can get overpressured, the velocity in the shales will reduce. So that's one type of signature. That's called rapid sedimentation. The other reason for pore pressure, we call type 2, is that sedimentation has already happened. And then something happened in the formation to increase the pressure. Let's take an example. You have got a sponge full of water, and you have covered it with plastic. And I squeeze that plastic bag or that balloon with water, uh, squeeze it. So the pressure inside that balloon is going to increase because it has no way to escape. But that pressure buildup has happened after deposition, where tectonically that formation is getting squeezed. So that is one type 2. Another type 2 is where you have the formation of a shale, like a shale, a certain types of shale can get heated, and thermogenically that will release waters of crystallization, typically smectite going to illite, possibly. So that releases waters of crystallization. That water builds up pressure. All these changes in the shale, adjoining shale, can be predicted from sonic signal. And that prediction, then we can relate that to the adjoining sand zone. Because the sand zone, you cannot predict or model for pressure through these intangible ways. So we have to look at the sonic signature in the adjoining shale to predict that that pressure from the shale might have oozed into the sand, and therefore the pressure could have built up. So such predictive methods are used. It's a very involved area. A lot of methods are there, but this will give you a bit of a flavor of how this pressure is derived.
Thank you for that answer. And I hope Devika likes your and got the information what she need on predicting overpressure areas. Because of the time concern, there is another question in the chat box, but because of the time concern, I'll be moving to the next speaker. Thank you very much once again for Zach to giving a very good narrative geomechanics models and applications into the drilling. That was a wonderful talk. So next, we are going to the third speaker of the day, and this session is on development stratigraphy and sedimentology. So our third speaker or third presentation, we have Professor Simon Lang from Perth, Australia. He will be presenting on the subject on fluvial deltaic analogs and their application to reservoir characterization. As I'm well known, Professor Simon Lang is a sedimentologist, stratigrapher with more than 40 years of global experience, including regional geological mapping, sedimentology stratigraphy research, and petroleum exploration and development. He worked at the Geological Survey of Queensland from 1979 to 1992. he had a very good experience with the Geology Survey of Queensland. Then he moved to Queensland University of Technology as a lecturer and associate professor in the University of Adelaide in 1992-2005. During his entire career, he worked on modern and ancient fluvial deltaic and deep marine deposition analogs and sequence stratigraphy for reservoir characterization, including CO2 sequestration. He also consulted to industry and gave numerous short courses to Southeast Asia, Japan, India, and Russia. He is well known in India as well. He was the manager of stratigraphy reservoir analysis team for Woodside, one of the oil and gas mining company in Perth from 2005 to 2013. Then he moved to Chevron oil and gas industry as a senior stratigrapher with the seismic geomorphology and classic stratigraphy teams for Chevron Energy Technology Company, Houston. And then he moved down to Perth in Australia as a geologic service manager and stratigraphy advisor during 2013 to 2018. He joined the University of Western Australia as professor of petroleum geoscience and director of Center for Energy Geoscience, leading industry-funded research consortia on seismic stratigraphy and reservoir analogs. He has published extensively and supervised numerous graduate students, led industry-oriented training courses and research consortia, and run numerous field courses and core workshops. He was PISA Distinguished Lecturer for 2010 and a member of PISA, APG, and SEPM. Moreover, he was my supervisor for my PhD and a great friend for all his students. And I'm sure he'll be going to be a great friend of all the attendees who is going to attend his talk. Please welcome Professor Simon Lang for his talk.
Thank you very much, Saji. Can you hear me?
Yeah, we can hear you very well.
Now I'm just going to thank everyone, the organizers, for arranging this. It's very interesting. I only heard the latter half of the previous speaker. I'm sorry, Zach, but it was very good. And you ended exactly where I wanted you to talk about integration into models, because that's where I'll be ending as well. So thank you. Saji, I'll just need to share my screen, right? So I'm just doing that now.
You go to the bottom of that. Yeah, that's right.
Now, can you see what I see? Is everyone seeing the title page? Fluvial deltaic analogs. Well, thank you very much. Hopefully everyone can see this. Good evening, everybody. I'm not sure how many people we have online, but wherever you are, there's quite a few names there. Thank you for taking the time.
That's a people online. It's more of like young professionals and PhD students, and the graduates and master students are watching through YouTube.
Well, fantastic. Hi, guys and ladies and gentlemen, wherever you are. I hope you're all safe. Okay, so what would like to talk about tonight is one of my favorite topics, which is fluvial deltaic reservoir analogs and how they can be used for a variety of things, particularly reservoir characterization and modeling. And the emphasis is going to be more on the analogs and a little bit less on the reservoir characterization at the end, mainly because of time. So I hope to show you lots of pretty pictures, if nothing else, so that you can keep awake and enjoy it. So let me just see if I can get the, there we are. So, okay, so the brief outline of what we're going to talk about today. What am I talking about? Depositional analogs, what are they? Why do we care about them? What's the purpose of it all? And then I'll talk about fluvial deltaic depositional systems. I'll give you a sort of a soup to nuts rundown on the main salient features of them, the critical reservoir elements, particularly distributary channels and the river mouth bars where the sands are debouched, like in the background picture here. And then we'll talk a bit briefly about some of the facies and discuss architecture and the importance of the geometry of some of these features and understanding them for for making subsurface reservoir models. I will briefly touch on the importance of accommodation. That means basin accommodation, which of course controls what's going to be preserved and so forth. And then I'll wrap up about how we can use some of these metrics and ideas and concepts for stratigraphic frameworks to bring into reservoir models, particularly static models. So I've been working on these modern analogues and ancient depositional analogues for the purpose of exploration, not only for oil and gas, but also for minerals as well. For many years, that's been something that's been my main thing I've been working on since the 1980s. And I just want to acknowledge my various co-workers. There's a whole long list there, I won't read them all out, but particularly the top line there, the late George Allen, who I worked with on the Mahakam Delta, Henry Posamentier, who's over in the US, and I worked with him in Chevron and also in Indonesia. My colleague Bruce Ainsworth, who I worked with at not only Chevron, but also before that he replaced me at the University of Adelaide, and various other colleagues, Toby Peinberg, John Holbrook, Steve Aziotis Kassan, and many others, my postdocs and my students, including, of course, Saju, who's not on this list, but I know we worked on many other things to do with reservoir characterization. The sponsors of my research work are Chevron, Santos, Total, Woodside Energy, and several others. And I thank them for all the support and their support. So let's get to the matter at heart. What are depositional analogues? Well, depositional analogues, and I'm thinking here both modern depositional systems and also the buried equivalents, the ancient depositional environments that we see in the rocks. I see these as all analogues or depositional analogues for our reservoirs. And what they do is they provide a conceptual framework that we can think about what the subsurface disposition of the reservoir rocks are based on our understanding of the processes that formed them. And so we have over on this right-hand side here, this concept of having analogues to help us think about our data and to constrain geological data. And they can help do things like, if you understand it and how an analog works, you understand the relationship between data points, this can help you constrain correlation between wells, because you can correlate things at a sensible scale, not correlating things over hundreds of kilometers that can only be correlated maybe tens of meters. This is important variation at the field scale. It can be used sometimes to help explain patterns that you observe in the seismic data, particularly the seismic geomorphic patterns. It can help visualize the reservoir geometry and connectivity for the 3D modeling enterprise, like what's connected to what. And it can help you explain and predict reservoir quality trends and production histories. This is a whole topic on its own that I know Saji could talk about extensively, Saji Menacheri. I'm only going to touch on it very briefly. It's a big topic. I don't have the time for it, I don't think. But I think if I was going to leave you one message, and that is that you have to take care in analog selection. They need to be sensible based on the observations and on the tectonic and climatic situation that was going at the time of the deposition of your sediment in that basin. And so there's no such thing as a single analog. There's no one picture, one concept, one data set. It's a range of concepts and data sets that you need to use so that you have multiple ideas and working hypotheses in your mind when you're interpreting your data. But armed with this type of information, you can use analogues to guide understanding of reservoir stratigraphy. So that's all the various time slices or layers in your model. And you can use the observation of the size and shape of the features in these depositional systems to get a handle on reservoir geometry and also heterogeneity at the reservoir scale. And then all of this part of the triangle then gets flipped over and fed into the reservoir characterization workflow that, combined with reservoir quality information and fluid information, then goes into those reservoir models, those subsurface models that Zach was finishing on at the end of his talk. So why do we care? Well, look, essentially we care because we use them to manage uncertainty. The one thing that you do know about the subsurface is that you don't know very much about it. That's the honest truth. We drill wells, which are a few centimeters across. We drill them for quite a long way down, but they represent 100th billionth or more or less of the actual full three-dimensional volume of the rocks that usually make up our oil and gas fields, or in some cases our CO2 sequestration sites, or even the aquifers that we draw our water from. So we often think we know more about them than we really do. But the one thing that we can use analogues for is to get a handle on, the spatial variation in depositional environments. For example, on this picture on the right here, you can see this is a river. It's called the Gascoyne River here in Western Australia. We're studying this at the moment. There's clearly a delta in the front of it, down here on the coast. And next to it is a beautiful beach ridge strand plain that goes for tens of kilometres. It's all excellent sand. To the south is a muddy tidal flat area that leads into Shark Bay, which is an evaporative basin. So the river more or less bisects a zone of excellent reservoir potential to the north and horrible reservoir potential to the south. And the change that can take place across that can happen in hundreds of meters to kilometers range. And it can be quite radical. So if your field is in the middle of that, one half of the field could be the poor stuff and the other half could be the good stuff. But the good news is that what we learn from analogues is that some depositional systems are very, very large, and they're much larger than the field. And sometimes we worry unnecessarily about the extent of things because the field is in very, very small relative to the size of the system. So we use analogues this way, and they are kind of like snapshots of the state of play at any given moment in time. Today, sea levels are high, they're not low. So they're only really a representation of a high stand world of sedimentation catching up with a very recent sea level rise. And so we know that there will be limitations, and we know that when sea level was lower, the disposition and style of many of the coastal river systems were different. They were often much more sand rich, much more sediment supplied because of the slope. And so we have to take that into account when we think about our analogues. But if you think about what the processes are, you can make some modifications accordingly. So this is essentially why we do it, to manage uncertainty. Now, just some 101s for those who may be joining that might not be too well versed in all of this, but I hope most of you have done this at some point. Let's just a quick recap on what we're talking about. We're talking about fluvial deltaic depositional environments. And I really mean the delta part rather than the river part for this talk. But you can't have deltas without rivers. That's essentially the main difference between a delta plain and a coastal plain, because the coastal plain is fed by only small rivers that usually drain directly and are not part of a larger river network. And so the sediment supply is usually different. And there are not distributaries. There's only single river systems feeding them. And so fundamentally, we have here in this gross depositional environment concept diagram, which we've drawn here, that we're talking about a tract that goes from the alluvial plain into this green area, which we call the delta plain. Here's the alluvial plain. Here's the delta plain on this analog from the Zambezi Delta in Mozambique. And you can see that across this plain, you change from a radiating set of rivers forming this cone, which represents the alluvial plain that's built out as the deltas have built out into the ocean. And in front of it is the active deltaic plain, where the rivers are building these low-bait protrusions into the ocean. These are building out what we call the delta front, which is the submerged portion, which is underneath this dark green here. Here it is on the diagram. And in front of that, of course, is the muds and silts that get dropped out in what we call the pro-delta platform, which is usually runs off to some tens of meters, sometimes even 70 or even 100 meters, of silts and fine sands that get deposited during the big floods. So we've got this very simple concept then of alluvial plain, the delta plain, which we can subdivide. I'll talk about that in a moment, and the delta front and the pro-delta. Okay, so if we use this this general concept here, just putting it in a slightly different way, you can see here's a fluvial dominated system. We've got a fluvial axis running down, bifurcating here at the head of the passes, usually about where it hits, just above sea level. And this would be where the ancestral delta was. And the system has then built out multiple little delta lobes with time, building out this much larger fluvial deltaic fan-like feature, which we call, of course, a delta. And the delta is actually a big thing. And inside the delta, there are individual discrete active deltas that are represented by a series of distributary channels and a series of mouth bars. And what really governs the most that governs the operation on these deltas is the landward limit of the effects of tidewater and also backwater. So when a river is building into the sea, the river feels the sea. It feels the sea because the bottom of the channel on land is deeper than the position of the shoreline, at least for a while. And once the river goes right through to the ocean, of course, all of the channel is below the sea level. So there's a point somewhere upstream where the channel's base is above sea level. And at that point, there is no backwater effect. Okay, and so you have this interesting combination that if the tube of the distributary is connected to this enormous ocean, it can feel the pressure of that sea. And as a result, it backs the water up and the rivers slow down. And as a result, they deposit their sediment on the delta plain. And during floods, of course, they can break out. So if it's connected to the ocean, that means it can be connected to the tides. And so there's a place, usually some tens of kilometers up, where there's the maximum tidal limit. And it can coincide with the backwater limit, although typically the backwater limit is usually further inland. And then there's this landward limit of brackish water, which is where ocean water is mixing with the fresh water, and this makes it brackish. This is important because it completely changes the biota that bioturbate the sediment and mix up the sands and muds, homogenizing them, and that's important for reservoir quality that we'll talk about later. And then finally, there's the true intertidal zone, which is submerged every day, basically, in and out of the tidewater. Half the time it's below the water, you don't see it, but it's during low water, it can be emergent. And this is where you can begin to see the river mouth bars that are being deposited right at the front of the delta front, but usually where they're slightly emergent and hence plants grow on the apex of them. And then below that, there you go off into the main delta front, which is where most of the active sedimentation is. That's the gray area here. And that's affected by two important things, the fair weather wave base and the storm weather wave base. And these are mostly impact, of course, what we call the shore face, which is further lateral along strike in the coastal plain. We're not going to talk about shore face deposits because they're related, but they're the downstream end game of these deltas. But the fair weather wave base impacts the delta front. So every day waves break on that front of that delta and they migrate sand around, and those sand then gets moved by wave processes that can smear the sand out. And they also get moved, of course, by tide water as well. During big storms, these delta fronts can be smashed by the storm waves, and the sediment can then be swashed out to sea in the form of what we call tempestites, or bottom-hugging turbidity flows, essentially, or density flows. We won't talk too much about those either. But as you can see from this general diagram I've got here, that you can kind of see how laterally the whole fluvial deltaic system passes to the interdeltaic coastal plain, if you will, with its shore faces and its offshore and its offshore continents. Now, most importantly, in the last 10 years or so, the thing that's really changed, and something if you haven't done your reading in the last 10 years on deltas, you can brush up on this. This is the work, a very important work done by Bruce Ainsworth, William Vakarev, and his many other co-workers. And it's essentially taken the old ternary diagram here, which is the fluvial wave and tide ternary diagram that was originally applied to deltas by Coleman and Galloway and many others in between some 30 or 40 years ago to explain the various river-dominated deltas like the Mississippi, wave-dominated shorelines, and so forth, tide-dominated deltas. But now this has become quite sophisticated now because of the understanding that there are mixed processes always at work. So most of our FASES models over the last 20 or 30 years were based on the end members. A river-dominated end member, a wave-dominated end member, and a tide-dominated end member. But we always knew, of course, that there were these transitions. This was not overlooked by the early writers. In fact, it was completely understood. But they weren't documented very well because there was only half a dozen of these key things that were properly published. And since then, there's been an enormous literature that's looked into this. And we now understand that mixed processes are important. So what Ainsworth and others have done is they've developed a hierarchy of sedimentary units based on things like elements and element complexes and sets of them, and then even assemblages of complexes. And they see the depositional environments in terms of these larger architectural packages, which we call element complex assemblages, these so-called ECAs. This is a diagram of all the plausible sub-portions of this diagram. Over here, you can see there's the classical fluvial-dominated delta, like the Mississippi, with multiple distributaries and protruding distributaries with their levees, the classic bird's foot delta. But we all recognize that as you power up the tides or power up the waves, so you modify those deltas. And it's the modification of those that are important for reservoirs because you move the sand from the front of the mouth bar around the delta, and that's important. And equally, if you just keep the logic going and head off into the deltas that are smashed by waves and run back this way, you essentially smear them off laterally until they just become a beach like this system in here, right? And then, of course, you can crank up the tides and play around with them and turn them into tidal coasts, and then eventually into funnels completely, particularly during the transgression. This is very important. The top section here is largely produced during sedimentary regression when the sediments are building into the ocean, and the lower segment is very common during transgression. And so the deltas are really just these guys. They're just these ones which we're going to focus on today, these element complex assemblages that are either river-dominated, totally, or various forms of mixing of fluvial and waves and a little bit of tides. And so the alluvial plain then is this uppermost segment sitting in here, usually the section that comes out through the valley, which is inevitably, there's usually an ancestral valley involved in big rivers, and even small rivers can have valleys like these ones, using the Zambezi here as an example. And there is a point, though, where the river exits the main structurally controlled valley, where it's free to move around. At this point, it produces this cone called the alluvial plain. And this alluvial plain will be built by radiating distributors of these rivers, multiple distributaries of the major river. The river that we know its name will be one of them, and it'll get its name like this one, the Zambezi, which makes its way all the way to the coast. But you can see from this satellite image, this is actually a topographic data set, a DEM, that there were multiple pathways of the former Zambezi. You can see them all racing around the landscape. And so this is a distributive alluvial system, right? Or a distributed fluvial fan, as it's often called. Various names for them. But this is where the alluvial system is, and this is where the river channel belts are. The floodplains are between them. There's lots of little tributary channels if it's entrenched. And then down in the main system, lots of these channel belts. They can range from being quite straight to fairly sinuous belts, as well as the channel within them. And they're separated from each other by floodplains and soils. And when you get down to the delta plain, this is where the real delta begins. So strictly speaking, this is the only real delta bit. Once the effective functioning delta is the little bit right at the end here. The whole thing is called the delta, of course. That's the name we generally give it. But it's actually broken up into these different depositional systems. And the active delta system is just this part, which is building with multiple distributaries into the sea. And they produce these low-bait mouth bars at the front and wing-shaped appendages on the side as the mouth bars are moved around by the waves. Now, these waves will chop off the front of these deltas. This is active at the moment. But an old delta used to be out over here. You can see it used to probably come out this way, and it's been destroyed by transgression along the coast. And it's been beveled back, and all the sediment has been migrated along, and it's now forming a coastal plain. And so it's no longer a functioning delta plain, it's actually now a functioning coastal plain. And rather than having distributaries, it has small rivers which are functioning as largely estuarine channels. They're not flowing river water very significantly, except during very significant downpours. And this is where the tides play their most significant role. Something else that just to appreciate then that these mixed influence systems are the dominant mode. Now, just moving along then, you can see the coastal plain has these many wave-driven spits that can migrate laterally, and these protect the former marine water, which then becomes a lagoon, of course, and behind it is where the coastal plain marshes sit. Now, this system can be confused with a proper delta. We would probably call this a wave-dominated shore face, and these spits and things we might call washover fans, a variety of things we can call it. But typically, these are just down drift from the outfall of the sediment that's providing it. So if you see one of these coastal plain strand planes on seismic data, for example, what you would infer is along the coast, there should be a delta. And the trick, of course, is to look for the muds. That's the part that really makes the difference. So if we consider, for example, since I know this conference is hosted in Kerala, if we go to the other side of India, of course, I've turned it upside down. And this is actually the famous Mahanadi river system, which is a monster of a delta that's prone to very, very dangerous flooding. For those of you who live on the Indian subcontinent, I'm sure you know all too well from the news that when the big cyclones hit the Bay of Bengal, this thing fires off and causes tremendous destructive flooding. But it's also the reason why you can grow a lot of good food there. It's very big. There's a 20-kilometer scale bar. It's about the same size, actually, as the Zambezi system. But you can clearly see how the rivers are coming out from these structurally guided valleys. They're forming a radiating network in the alluvial plain, and then they branch into multiple smaller distributaries. You can see them branching out here. And these are the distributary channels of the upper delta plain. I would call them distributors because they're big, they're full rivers in their own right. And then they break up down dip into smaller distributaries. They're distributary channels, which are down here in the lower delta plain. And this dotted line is the approximate line of the daily reach of every high tide. But this region is anastomosing because it's feeling the backwater and some of that very large tidal range. Right out the front, you can see the effluent plume beautifully here, building the mouth bars. The mouth bar is there. There's a mouth bar there. There's a mouth bar there. But of course, they're being smudged by the ocean, which is building by waves coming through the Bay of Bengal and pushing that mud out to sea, building that pro-delta. So a good way of just sort of rationalizing, even though these are two deltas look superficially different, they're actually basically the same. They're both wave-dominated, fluvial influenced and tide-affected river systems at the macro scale, the element complexity scale. Now here's our old friend, the classic fluvial-dominated delta, which we would have all learned about in textbooks. I think we could see it, a distributary channel axis with multiple distributaries and shallow triangular mouth bars. This is the typical shallow water friction-dominated mouth bars we see. But this is actually the dominant mode that you get along the Texas coast and many other coasts. And that's actually just around here. This one is actually a man-modified channel, actually. The natural one is here, the Echeverria system is here. But there's the big boy Mississippi protruding way out into the ocean, obviously one of the world's largest rivers, with an enormous discharge and enormous sediment load. But it's actually unusual, right? And so like a lot of things that get written up in the land of US&A, people work on the Mississippi. Lots of people have worked on the Mississippi. It dominates the literature. And so it takes on a life that's actually larger in the literature than I think it actually deserves. And that's obviously the reason they've done the work, is because of the tremendous importance it is to the Gulf of Mexico and, of course, to towns like New Orleans that are, of course, in the process of being drowned by the sea. But you need to just remember that most of the river-dominated deltas are not these big, tall levee-based systems like the Master Mississippi. They're actually shallow water, fluvial dominated deltas like the guys here in the bays. If you go and have a look at the fluvial and tide dominated deltas now, which is one of my favorites, which is the Mahakam system, because I've worked on it with George Allen and Toby Pineberg and others. And it's sitting over here in Indonesia in East Kalimantan. And you can see the river as a major axis, which comes out and it bifurcates here at the head of passes. This is where the delta was about 8,000 years ago when sea level had reached its maximum height. And it's prograded 70 kilometers in less than 8,000 years. It's a phenomenal system. And you can see it's got multiple distributaries. It wants to be a river-dominated system, actually. But because there's enough tide water in the Makassar Straits, when the channels switch, the old channels become immediately impacted by the tides. And so they function as tidal estuaries in their mouths when they're abandoned, like here or over here. But when they're fully active, they produce active mouth bars. At the moment, it's the southern system, this is rotated, it's active, and the northern system that's active. The rest are all moribund. And so it flip-flops between being river-dominated and tide-influenced through to being tide-dominated and river-influenced. There's no waves, though. You can't go surfing in the Makassar Strait. There's no waves to go on. There's a tiny amount of wave power, and it moves some sands further south, but mostly it's really, we're talking about an F and a T system here. And it's got these very, very long, rather straight distributaries, and they're very sandy. We know this because we've cored them. And you can see them in outcrops, and they produce these rectilinear channel bodies. This is a paper from Toby Pineberg and myself some many years ago. And these are full of sand. They're about 20 meters deep. They're very, very strongly flowing. And when they get abandoned, they leave these great tubes of distributed sand in the 3 dimensions. And at the toe, at the mouth, they have these enormous mouth bars. This is 6 kilometers across here. And we cored these, and they produce these classic heterolithic reservoirs. They tend to have little short thickening upwards and sanding upwards packets that then become switch-swatching around as the mouth bar is moved by the river action. And so you get this classic heterolithic succession. And they're quite vertically, the vertical perm on them, permeability is very challenged. But they are very important gas reservoirs. Here's another one that we're just beginning to work on now. There's a new system that's nothing's published on it of any consequence. We're just going to start coring this system in next year. And this is the De Grey River on Western Australia. It's a brutally hot, very remote region of Western Australia, north of the great iron ore mining district of the Pilbara. In that sense, it's almost like a counterpart to the Mahanadi system, except it's much drier and much hotter. I noticed it was 40 degrees there today, Celsius. So this system, water doesn't run very often, but when it runs as a giant flood. And then dumps a lot of its sediment during a brief fluvial dominated phase, and then spends the rest of its time being modified actually by tides. So it becomes a tide dominated and even wave influenced system, and almost small fluvial action actually associated with it, but not because of the volume of fluvial action, it's just the time. It doesn't take very long to work on them. And so we begin to work this, and they produce these enormous downdrift. You can see here's the downdrift reworked portion of the mouth bar, which is enormous. This is these scale bars, these are 10, that's a 10 kilometer block there. These are big, right? This thing goes for tens of kilometers, and it's largely fine sand and silt, and would be a low deliverability gas reservoir when it's buried in the subsurface. But it's hinged to this excellent quality reservoir right at the mouth bar itself, which is made very large by the actions of the daily tide. There it is in the center. So we'll be working on this more as we go over the next few years. We're looking forward to this. In fact, this is part of my current research. So they'll put a little advertisement in while we have a breath for fresh air. And so these are all these deltas on the West Australian coast, which have had almost nearly minimal to zero studies on them. But we think they're important because these dryland so-called deltas are underrepresented in the literature. And they're great because the rivers flood and then the water evaporates. So you can actually see a lot of the depositional products by walking around after the flood. Whereas most of the active perennial rivers, you can't do that. You need to get boats and do submersible action in the delta front or in the channels. The water runs right through them and out the other end and then leaves the channel behind. And of course, there are a lot of rivers in the Indian subcontinent, in fact, all through, even into the Arabian Sea, several parts of Africa, the dryland parts of Africa and South America. So this is a common feature actually, but we've got a lot of them here in Australia and we're working on these. We're interested in how the tides are making these river mouth bars much bigger than the scaling that you would normally address to them. So this brings us to the important issue really of architecture, because, you know, as I mentioned earlier by the Ainsworth and others study, they developed this hierarchy of elements, element complexes, and assemblages. And they did this in order to try and make some kind of proper sense of measuring the very detailed features that you find on these modern deltas. This is the Mitchell Delta from Northern Australia. And it's a very, it's another one of these tropical monsoonal systems. And you can see when you look at the geomorphology map here, that there is all these long linear beach ridges that are very important and very sandy and would be future reservoirs, nice shoreline reservoirs. But barging through this is the channels themselves, pushing their mouth bars in front of them, and downdrift from them are these tidal flats. And so you have a situation in a mixed system like this where you go from quite good reservoir potential almost across the channel, and then it's very poor. And this is important because if you drilled the channel belt and you thought you had excellent sand on either side of you, you could end up the next well going straight into a tidal flat for that level of the reservoir and being very disappointed. So we do need to understand these systems. And to do that, what Ainsworth and others did was they broke up this triangle into a kind of Toblerone-like feature, and to consider all the elements that we can measure in these modern analogs, right down to the individual elements like a beach ridge or a channel. And then we package those into element complexes, and then we package the complexes into sets and then assemblages. And it's those assemblages that make up the stratigraphic units that actually are the reservoirs. So the reservoir is not the individual element. It's not even a set of them. It's actually a whole layer. And so whilst we've got data on all these individual elements, which is all very interesting, that gets you to the information about heterogeneity, but it doesn't get you to information about lateral extent. So to do that, you need to start thinking like this. You take a map like that, and you divide that up into the element complex sets, or element complexes, as we call them. So these are not individual sand ridges, these are sets of them. And you sort of can just focus on just the channels that are building through them as they grow. The channel obviously got to this point, was a delta was right there, and this is the downdrift section. Then the channel avulsed and went to here, and then avulsed and went to there, and so on and so forth. And so if you even simplify that even further, it's a sheet of sand and mud and silt tagged together into an element complex assemblage, which has been laid down during the regression. So this is the layer of sand, or the reservoir layer, that we would consider in our correlation. But this is actually what's inside that layer. So if you've got maps that just show everything as lovely sand, and then you realize that it's actually built by something like this, you're going to have a different appreciation of heterogeneity. And so this is the scale that you need to model at, is this element complex scale, but you need to create your frameworks at the assemblage scale. Now, I'm not going to go any further than this because this is really their work, and just bring your attention to it, but it's gone a long way. They've built enormous databases. They've measured everything that you could measure. It's all gone into these enormous data sets that you can look at the size and shape and thickness and width of all the features, and it's all been published in various ways. And I just draw your attention to it. There's whole online data sets now for all the different types of deltas, channel parameters, how deep, how wide, mouth bar width, thickness, and so forth. So we don't actually need necessarily to go and repeat all these systems, except for those that are unusual and have not been adequately described, hence the dry land system. Now, what we can learn from this is we can learn a few things. For example, here we can see how seismic data can now be interpreted. This is a huge image, by the way, 5 kilometers. So we can use spectral decomposition from this seismic extraction to actually look at the geomorphic features. And we can now start to identify some of these shapes that we've observed on those analogs and start thinking about what's going on between the coastal plain, the shelf, the slope, and the basin. And we can start breaking these things up in terms of their dominance. So, for example, we can see some rivers carving through here, building these gullies and turbidite down dip. We can see an whole river system that's building through here with perhaps some tidal influence, wave-dominated shoreline, and heading down to the sea. We can see some rather wriggling-looking rivers here. Got to get my mouse to slow down. Here, there's some channels just sitting in there. Right there, there's some sinuous features. We interpret these as channels sitting in behind the shoreline. I can hear someone's children. Hello, children. Time for bed, I think. Someone hasn't muted their microphone. Obviously, time to put the children to bed. So we can use those analogs to inform our seismic interpretation. So now, just switching gears a little bit, just now we need to move away from the modern systems briefly to understand stratigraphy. How are these things stacked vertically? Oh, I recognize that sound. That's the sound of little children. That's okay. Doesn't worry me, guys. I'll just talk through it. So when you look at the outcrops of the great deltas of the world, like this one in the Mahakam, which I know, the first thing you observe is that everything is very layered. Each delta is stacked on top of each other, more or less at an even thickness with subtle variations over significant distances. And that's why deltaic successions are often considered to be very layered. Seismic data shows very, very parallel reflections. But within those layers, there's a lot of lateral variation, okay? They're not consistent laterally everywhere in terms of lithology. They're consistent in terms of their stacking pattern, though. They tend to have a drowning surface, and then they fill in with the delta. And sometimes they fill in with tidal flats, or pro-delta shales, or distal mouth bars, or the distributary channel barges in, especially if it's prograding. So we can use these outcrops to really hone in now on the bigger picture. Imagine our well bore would be drilled basically through here. We get one sense of the well bore drilling through there. We cut right through that little fault. But here we can see we've got one delta cycle of the pro-delta muds building through the proximal pro-delta into the distal mouth bar, up into the proximal mouth bar, into the shoreline, and even mixed in here with some carbonate matter before the next flood. And we can see the scale of this. It's about 10 to 25 meters, which is approximating the water depth, allowing for compaction of those muds that this system built into. And as a consequence, you can sometimes see, I've just rotated this around, that there are growth faults that pick up as that mud compacts with the sediment load. And you get all these interesting structural stratigraphic effects, which I'll pass over briefly. But what you get in the end is a stacked delta cycles that represent the lateral switching of the delta, as well as the rise and fall of sea level. But mostly the sea level could be continually rising. It's just that it's being filled continuously with more or less amounts of sediment, and the whole system is prograding further into the ocean. And so what you see when you deal with fluvial-deltaic systems in the mouth bar section, for example, are these short little sections, little cycles of a flooding surface, pro-delta mud, building up to the shallow delta front, and sometimes even the lower coastal plain, bringing the coal with you, tracking as a shaly, coaly bed over the top of the delta. And then you get the flooding surface over the coal. So the coal is not in the marine system, it's the emergence part of the top of the delta plain. So the delta plain is actually muddy right in this section. And they tend to look like this in core. In the seismic expression of these, I've got some good examples from deeper ones, but I can't really show them. But I found this is a nice one from the Mahakam system at about 100 milliseconds below the seabed. And so you can see this Pleistocene triangular mouth bar here. There's kilometers for scale. So this is like 8 kilometers across. It's a triangle, and there's a lot of good sand in there, and it's separated by these distributary channels and the various coastal plains around it. We can see that in the modern environment today. There's the modern mouth bar forming. There's the ancient one. They're even almost the same shape, slightly different place. And it's formed as a consequence of the river coming out, dropping that sedimentary load into the water body, decelerating water flow, bifurcating the flow, building the bar in between as a stream mouth bar. And eventually these distributaries will lengthen. And at some point, one of these distributaries will become inefficient and it'll get abandoned, and that will get cut off and become a tidal creek, and the river will then start to bifurcate again. This is typical. And what we find about mouth bars is that for each meter of section that's deposited, they're about 1,000 meters wide. They can be wider, of course, or even narrower, but typically, if you had to walk away with a number in your head, for every meter of stacked mouth bar you can get 1 kilometer wide on the wide axis here. And they can be many kilometers long, depending on how much tide action or how much wave action. So these are big sheets of sand, right? And they can produce these whole element complex assemblage layers of mouth bars as the delta builds. And in core, of course, we see them. This is the classic profile here, a coarsening upward succession of mud and silts, cleaning up to sand at the top, and then either a flooding surface or sometimes the coal can be attached. And then if they build into the bays on either side, they can be a lot more complicated. You can get sort of more like tidal flats and things represented by them. Meanwhile, out in front of the delta, you've got these muds that are being deposited by flood events. They're little hyperpycnal flows, as we call them. They got these density flows that flow as undercurrents, and then you get a lot of suspension fallout on top. And they tend to be very muddy. They're not reservoirs, really. They might represent some kind of unconventional reservoir, perhaps, but they're not conventional reservoirs. Whereas the mouth bars tend to be excellent reservoirs for gas. The distributary channels, just again to give you a picture of one so we can see what we're looking at here, and you can see that they're very sandy. They're full of cross-bedded sands, sometimes quite coarse-grained. They stack. They can usually got a sharp base, and they're full of cross-bedded or low-angle bedded sand. And as they get abandoned, they tend to get biodebated at the top. Now, the thing about these distributary channels is that they are in 2 parts. There's a proximal part, which is up on the delta plain, in the upper delta plain, which is, for all intents and purposes, a river. It's just a river like anything else, right? But they are functioning distributaries. And the other part is the lower delta plain, where they tend to get abandoned and biodebated by various bugs that live on the bottom of them. And so they tend to be these rectilinear features, and they can be separated by each other by floodplain deposits of one kind or another, and soils and crevasse splays that are produced during the flood cycle. But they tend to have excellent sand, and they can actually be, we know of distributary channels that are easily 20 meters thick and sometimes even 40, especially in the upper delta plain, just right where the river is exiting. And we know from the seismic data that we've observed, this is the seismic extraction from a Triassic distributary channel, and it's the same size and shape as now modern ones that we can see around for similar scale systems. If you had to take some numbers away, the distributary channels are narrow. So they tend to be sort of like somewhere between 1:40 and 1:100. You know, the mean of them is about 1:70. So for each meter deep, they can be about 70 meters wide. And so really, really deep ones can get up to a couple of kilometers wide, but typically that's it, okay? So whereas fluvial channel belts can be many, many kilometers wide, tens of kilometers wide in some cases, or certainly many kilometers, the distributed belts tend to be 1 or 2 kilometers. And when you track them from the upper delta plain down to the lower delta plain in log expression, this is sort of some just plucked out samples. They're very grained and stacked crossbed sands by the dunes that are in them in the proximal environment, and they can stack up to quite thick. Obviously, there's multiple channels here. And as you go down several tens of kilometers or hundreds of kilometers, they start to get a little bit more discreetly finding upward, and they're often biodebated at the top. And eventually, when you get into the lower delta plain, They can be quite small and often are filled with mud because they get abandoned. There's a variety of different log motifs here. They tend to be blocky over here in the proximal zone, breaking up into discrete or finding upward cycles as you come down to the bottom. And then not to forget just for a moment, though, that the bulk of these deltas is actually mud, right? So if you go to a delta, any active delta, the thing you notice if you step out of your car, you step straight into the mud. You don't step into the sand, you're in mud mostly. And it's on these floodplains where most of the water spreads out during the floods, and that's where the silts and clays go. And as a consequence, there's a vast amount of muddy soils and peat bogs and so forth, which can make coal in these delta plains. And there's a variety of ones which are well drained in the upper delta plain, and they can be soggy and brackish in the lower delta plain. A whole talk on that, which I'm not going to go into, but just to remind us that we're interested in the reservoirs, the distributor channels, and those mouth bars, but it's the other stuff that causes problems because these muds can be very stiff and they can be very strong intraformational seals between the distributor channels. So if you actually look at seismic expression of some of these are some examples from the Triassic of Western Australia. That's a 100-kilometre scale there. That's an enormous seismic image, a massive 2D, 3Ds put together by some people at Shell. And all these worms here, all these enormous amounts of worms are hundreds of distributor channels in an optical stack. So this would be a 200 or 300 meter millisecond thick stack of seismic in which there's countless channel belts that have wiggled their way through this bit of geological time, probably representing at least a million years of delta progradation. And we can use our understanding of the analogues to actually designate and peel out what's a proper channel belt and what's not, rather than just seeing it as a continuous layer. We do this. This has helped enormously in subsurface mapping. We've also, my colleagues at Chevron, Toby Pineberg especially, and others, we spent a lot of time myself measuring these. We've measured their channel belt widths, and we've measured their, by measuring their width, we've measured their sinuosity, their narrowness, and even the different styles. And we recognize by thousands of measurements that most of these channel belts are actually less than a kilometre across and don't really get much wider than about 2.5 kilometres, which is what we were saying before. And so they're discrete, they're tubular, they're not sheets, they're not layers of sand. And we also know that they have these half wavelengths, which can measure from the sinusoid to the sinusoid. And these give us the compartments. And we know that those can be anywhere from 2 kilometres to 10 kilometres long. So straight away, they can be 5 times longer than they are wide. Just something to think about for the size of the compartments. We also know that they're mostly low sinuosity. These are frequency distribution plots measured as sinuosity, and they're low sinuosity. So we can use this data, and when we pile all of this in to all of our well data across a basin, this is over 400 kilometre length across that image, you can see the well log style varies in the proximal zone from very blocky sands. Some of these may even be true fluvial channel belts, but we know that many of them are these delta distributaries coming out here. These are the yellow ones. And the river passes laterally down dip into the delta plain and eventually into the delta front. And we can track these between flooding horizons. And we have multiple stacked deltas. There's 1, 2, 3 deltas just there alone that we can divide. So the analogues can be now used to understand the variety that we're seeing in our data. And when we integrate all that information together, we can start making panels like this is a well panel, zigzag across one of these fields that we've recently developed, the Wheatstone field. This is work published by Ainsworth, myself, and others recently. And we've taken all these well data. You can interpret them by all of the facies logs, the cores, the reservoir quality data, that's these little pies. You can contemplate the size of these channel belts by scaling from the thickness. And then we can make these maps and use the seismic data to make a much better interpretation of the subsurface. And we, on the basis of this, we bring these into these reservoir models. And so at this point then, and coming to a close here shortly, the thing to think about is one thing is to deposit all of these sediments on a delta plain, but what actually gets preserved is something slightly different. If the accommodation is low, a low accommodation environment, all these different types of channel belts and various fluvial channels and distributaries will become vertically amalgamated. And so you'll get multiple systems amalgamated in each other. So they can become stacked, and you can't quite tell sometimes which is the individual discrete cycle. If this is the case, then vertical communication will be heavily enhanced, which is good for vertical communication. The more you increase the accommodation, though, the more each discrete system is preserved, which leads to increasing heterogeneity and increasing isolation of the channels from each other. And that can become problematic because it can lead to increasing need to drill more wells to connect things together. Okay, and you can kind of conceptualize that around the use of a conceptual analog. And another thing to think about is here's three little deltas I've drawn in a block diagram, each separated by a flooding surface. There's your alluvial plain, delta plain, your delta front. If the accommodation is high enough, you can stack each delta cycle separated by a marine flood. That'll be an excellent seal blocking gas or oil communication vertically. It has to track around horizontally and go through some three-dimensional network. And typically we notice that once the net to gross goes over about 35% in a well, then somewhere these sands bodies will be connected in 3 dimensions. If it's more than 50% of net in the well, then they're probably all connected somehow. So we use this data to bring all of this information together into these integrated static models, which I'm not going to talk about in any detail other than to say that all this data is brought in to condition what can be correlated sensibly in a reservoir model and to guide the properties that go with those facies. This is where all the reservoir quality information is brought together with the facies to make sure that we have an understanding of the subsurface reservoir. And then by using these ideas and concepts based on all the data, the cores and the wireline logs, all the petrophysical data and the reservoir quality information, that all then feeds in to these stochastic models that can be made that can learn from the data set. So rather than being just geostatistical distributions of data points, they can actually use the widths and sizes of the system based on the analogs to improve our subsurface models. So to conclude then, just coming up to 9:30, my time here, the takeaway messages for us all here tonight are as follows. That these depositional analogs, both modern or ancient systems, they provide us with a conceptual framework for interpreting our data. They can be useful as a tool for predicting lateral and vertical changes in lithology. So they're based on those lateral and vertical facies juxtapositions in the actual depositional environment where the processes are operating. They need to be thought of as a spectrum based on dominant to subordinate processes inferred from all the data we get in the well logs, cores and cuttings and so on. They can help understand seismic geomorphic patterns in the subsurface that may be a bit unusual, and they can guide exploration and even development drilling that way. We can use them to help appropriately package the rocks into genetic packages, little parasequences, rather than just lithological correlations. And of course, they're going to be different at different relative stages of the sea level. Low stands are going to have lower accommodation, high stand, they might be more isolated. Now, you need to then contemplate there's no one analog. You need to use a series of them to think about the range of uncertainty. And we use them to just assist visualization of the reservoir geometry, to understand connectivity, to constrain correlation between the wells, to build those subsurface static models. And finally, and not that I talk very much about it, but I put this one for you, Saju, is that they can help us understand reservoir quality because we can recognize the grain size variation and clay percentage variation in the modern environments, and we can translate that into the subsurface to explain our properties that we observe that sometimes can be difficult to explain unless you understand the natural variation. And so with diagenesis, of course, and different composition, this will impact on the actual reservoir quality, irrespective of the size and shape of those bodies. And so again, useful, but only when it's done with the other forms of data. So thank you very much for your time tonight. I can hear the children are moving in the background, or the wives. I'm not quite sure who it is. Someone's interrupting someone. Probably time to go to bed. So I'll leave it with you now and take some questions from you all. Hope you enjoyed that. Thank you very much.
Thank you very much, Simon. As usual, that was a great talk, and you take us through all the, entire system plus with all the modeling, all the logs and everything. So thank you very much. And maybe because of the time constraint, maybe we can take a, 1 or 2 question maximum.
Sure.
Please type any questions in the chat box, or you can unmute and ask question.
I don't see the chat box on my end here somewhere, Saji, but
so it's,
I'm
it's
sure
in the
you
bottom, but I can read for you. There is no question at the moment.
Right.
If there is no other questions, I would like to ask one other question. Your thoughts on reservoir quality. As you mentioned, like the facies of a fluvial deltaic depositional system versus the reservoir quality. So the time of the deposition, the reservoir quality versus on the burial diagenesis. Is it a much difference what you see, or it's almost the same, or what are the factors it's controlling?
Well, I think the question there is that, well, there's several lines to that. I think firstly, the lessons that we've learned from the analogs is that grain size and sorting can vary more at the short distance than it is at the longer distance. So, for example, if we took a dozen samples in this channel belt here, which I put on here, we can actually see that there is, if you just went there blindly taking samples and looked at them, you would see some variation, even a couple of standard deviations from the mean sometimes, depending on how far you walked and which way you walked. But the one thing you would be able to say is that if you were in the channel at all, that's the only place you're getting coarse grain sediment. Right? Where if you're outside the channel, you're only getting silts or very fine. And so this is obviously going to impact in the burial subsurface, because the clay entrained outside the active channel belts particularly will mean that the also finer grain sediment will be compacting, and that clay will be squeezed between the grains and will be tightly reducing the permeability from the beginning. And I think you know this, Saji, from some of your work, that it doesn't take that much clay to put in a sand to make a big difference to the way it will react. So the high energy deposits of the channel, distributary channel and the proximal mouth bar rinse all that sand out. And as a result, we'll get very good grain to grain contact. And this could mean that in the burial history, that those sands will being poorly, they're moderate to poorly sorted, but they might develop an early cement phase, which might lock the framework together. But still, if it's coarse grained enough, preserves still a significant amount of pore space, which then can be carried down deeper. Also, the clay sometimes can coat those grains, and you can get a little thin clay coat on the river generated sediments, and they can protect the rock from deep burial quartz occlusion of the pore space, because those clay coats can stop the diagenesis. I think the other thing is that the change in grain size from coarse to very coarse in the main distributor channels to fine to very fine on the mouth bar also increases the amount of feldspar. I think you and I have looked at this in Lake Eyre in Central Australia, didn't we? And that feldspar increase in proportion of the rock means that part of that rock can become more reactive and can convert to kaolin clays and other things later. And so it can end up being very useful in the deep burial. So I think there are lessons to be learned. I think the thing that we don't get out of it, though, is we're not including the other things that go with deeper burial, like the loss of water out of the compacting clays and various other subaqueous fluid effects, which we don't really see in the modern. We have to actually think about that. But if there's significant compositional variation laterally from one river channel to the next, we know that that can make a difference. But for example, the iron coatings is a case that comes to mind.
Yeah, thank you very much. That's a very good highlight and answer. Simon, because of the time concern, now it's like 9:40 here. We are like around 10-15 minutes ahead of our schedule.
Yeah. Yeah, that's real.
Shall we move to the next speaker? So once
Certainly.
again, yeah, thank you very much on behalf of the organizing committee and myself. Thank you, Simon, for your great talk. So we will move to the next one. Zach, could you
Thank
please?
you very much, everyone.
Thanks, Simon. Great talk.
Thank you. I'll stop sharing now, so it's back over to you. Is that you, Steve? I can see Steve there.
Yes, Steve.
Unmute, Stephen. Unmute.
So we see some very good backgrounds behind Simon and Stephen. So that's great. So we are in the last, we are the last talk now. And this session is on the development in stratigraphy and sedimentology. And I would like to introduce all of you to our fourth speaker today. And Professor Stephen Haziotis is a paleontologist, ichnologist from Kansas in USA. He will be presenting on the subject on the role of ichnology in the analysis of modern and ancient sedimentary systems. Now, Professor Stephen is a paleontologist, ichnologist with 35 years of global experience in integrating ichnology, paleontology, sedimentology, stratigraphy, and sequence stratigraphy in research that has taken him to every continent, including the South Pole and Svalbard. He worked 6 years in paleontology stratigraphy branch at the United States Geological Survey in Denver, Colorado, while completing his PhD at the University of Colorado in Boulder. He received his BS and MS at the University of Buffalo in New York. He worked as a postdoctoral fellow at Exxon Production Research Company in Houston, Texas for 3 years, and he taught at the Indiana State University in Terre Haute, Indiana as a visiting assistant professor for 2 years. Currently, he is a professor of geology at the University of Kansas, Lawrence. For 20 years, he works with geologists all over the world using ichnology to reconstruct paleo environments, depositional histories, paleohydrology, paleoecology, and paleoclimate. He has authored and co-authored over 500 papers and abstracts. He has taught over 50 short courses, field courses, and core workshops. He was elected a fellow of the Geological Society of America. He has done over 100 interviews for the public about significant scientific discoveries for national and international radio, newspaper, and popular science magazines. He appeared on the Nova Special Arctic Dinosaurs, discussing the significance of dinosaur tracks and invertebrate trace fossils as proxies for hidden biodiversity and indicators of ancient ecosystems and climate. He was editor of the international peer-reviewed journal Paleoes, and several on the other editorial boards. So we welcome Professor Stephen for the talk. We look forward to your talk, Stephen. Over to you.
Look like Professor
Thank you very
Steve
much.
is like a celebrity. He is
yes.
coming all the shows in TV, media, everywhere. Thanks,
Right.
Steve.
Well, thank you very much, Saju and Professor John Zach, for inviting me and for the organizing committee. It's a fantastic idea during these times to have this International Geoscience Colloquium, and I'm very humbled to be a participant. Thank you. Let me see if I could get my screen shared. I'm not very technological savvy. Let's see, share screen.
You should see it at the bottom, right at the bottom.
Here we go.
Yeah,
Share.
it's coming up.
And
Yep,
let me
you can see
see
that.
if I
Great.
can get my laser pointer.
No, I think you have to first put on screen mode. I think it's picked up something there. So just, yeah,
Right
you
click.
got it.
Then,
yep, got it.
Oop,
Just
no,
right
the right click. Where's the laser?
Yeah, right click there.
I think first you have to get it into PowerPoint mode.
Yeah.
So you show it in slideshow mode. I think you're clicking on the right,
Slideshow.
which is at the bottom. Yeah, that side. Or you can click on that icon on the bottom right.
Yeah.
That one, yes. So once it comes on slideshow mode, then you can right click on that slide. Yeah, now right click.
Yeah, my right click is.
Oh, it's not working,
It
is
makes it go, but no,
yes,
pointer
yeah.
options.
And
Laser.
Laser.
Use red, perhaps.
Yeah,
okay.
That would go.
Come on. Well, here, why don't we just get started and we'll just see how make do. All right. So what I'm going to discuss with you is the general role of technology in the analysis of modern and ancient sedimentary systems, providing you examples from marine and continental settings. But we're going to start off with defining technology and giving you some most up-to-date 21st century types of definitions and examples. So technology is the study of organism behavior and its products, trace fossils. A trace fossil is the product of an organism interacting with a medium in an environment that generates a three-dimensional physical structure. The organism, the medium or substrate, environment, and the three-dimensional physical structure are all scale independent in a sedimentologic framework, in stratigraphic framework. So why don't we define these terms so we better understand the definition? The organism can be any representative of the bacteria, archaea, or eukarya. This means any trace-making prokaryote, protozoa, fungi, plant, or animal. The medium or substrate can be the surface of a mineral rock or grain fragment or glass shard, like we see here, or they can be a mixture of sediments and moisture levels that can produce soup grounds, soft grounds, firm grounds, and hard grounds. Now these media, if they're rocks and hard grounds, they can be igneous, sedimentary, or metamorphic. Even organisms themselves can be a medium for recording traces. So they can be live or dead or post-mortem. They can be xylic or wood, or they can be endoskeletal like this, bones, or exoskeletal mediums. The environment is a location with distinct physical, chemical, and biologic characters that is found in subterranean, continental, transitional, or marine settings. And with this environment, that the interaction between the organism and the media is recorded, as well as organisms within organisms are recorded. And lastly, a trace fossil is a three-dimensional physical structure. That means tracks, trails, burrows, nests, roots, biolaminates, borings, and etched surfaces. These traces can be micrometers in scale to kilometer scale features. So for example, at the small end of things, here's an example of microendolithic borings and hyaloclastite from Hilo, Hawaii. Notice the scale, 40 microns. So these are borings in volcanic glass. On this end of the scale, we have vamporoid amoeba borings, predation boring drill holes in fungal hyphae. These fungal hyphae are part of microbial mats that build up one upon the other to build stromatolites, like we see here. So this is the small end. On the large end of the scale, we can have trackways and mega footprint trackways of dinosaurs and other large vertebrates, as well as fossilized termite nests and ant nests that can be traced over a cubic kilometer of sediment. A trace fossil is also a type of extended phenotype of the organism or organisms and its behavior, which can be used for proxies for body fossils. Trace fossils are often tens of millions of years older than the body fossil record itself, because you have only one body to give to science, but you can make hundreds of thousands of millions of traces through your lifetime. So the traces constructed by these organisms here at the bottom are reflections of their presence in the rock record. And we'll talk more about this as we go through. All right, so there are 4 guiding principles in ichnology. We'll start here. The first is one organism can make many different kinds of traces. So here we have a fiddler crab, and it makes a dwelling burrow, it makes a trackway, it can make feeding pellets, and it can also make fecal pellets that result from feeding. Though we have 4 different traces, they represent the same organism. In our next guiding principle, the expression of a trace or trace fossil in the outcrop must be examined very carefully, because what might look like 4 different trace fossils is actually 4 different preservational states of a burrow or trace in the bedding plane. So this may be the bottom, this goes through the center of the trace, this is the top, and then this is the very base looking at the bottom of a bed. In our third principle, you can have many organisms making a similar type of trace. In this example, we have the trace fossil called Rusophycus. It's a bilobate, bean-shaped trace that has transverse scratches on each of the lobes. In this case, this one trace can be made by polychaete worms, snails, conchostracan shrimp, as well as the now extinct trilobites. All right, so you may have this one trace, but could be made by multiple organisms. And then in this last case, you can have complex structures, but it doesn't mean it was made by one organism. This could be made by communal organisms that interconnect their burrow structures. So in this example, we have lobsters, crabs, and a goby fish that have these interconnected burrows, but careful analysis can tell you that these were 3 different animals making one interconnected system. So burrows are described by their architectural and their superficial morphologies. So though there may be a huge diversity of organisms that can construct burrows and trace fossils, there are only so many morphologies or morphotypes made. So we described their architectural features, their walls, if they have linings, if they have fecal pellets. And some of these burrows or traces are made by organisms that move through the sediment, either ingesting in the front or digging in front and packing in the back. And they make various features like menisci. Burrows can be complex, where they have vertical portions or shafts, horizontal portions that are called tunnels or galleries, and they can have various types of branching like Y branching and T branching, and they can have enlarged areas where they interconnect. These can occur in one or more planes. When you have complex burrows in one plane, it's called a maze system. If they're interconnected in 3 dimensions in multiple planes, it's called a boxwork. So some of these burrow morphologies can be simple, but the shape is translated through space and time. And this translation of a basic burrow creates what's called spriting. Right, so in this case, the burrow Tychicnus started here at the bottom, which is the subhorizontal tube, and through time, the organism moved the tube upward, leaving the previous bottom of the tube behind. So the end result is this pattern here. In the burrows Diplocriterium and Rhizocorallium, which are U-shaped, one is vertical, the other is horizontal. As the burrow is extended through time, the bottom moves down and leaving the previous position of the bottom of the burrow. And in this case, in Rhizocorallium, as it extends down outward, it leaves the previous position of the burrow. And in some cases, the burrow is expanded in multiple directions, like in Zoophycus, where it's expanded laterally and in widening directions. So the animal lives in a tube, but this tube at one time was here in the middle and has been moved outward through time. So with all these different morphologies, we can put them into categories of different organism behaviors, which are based on the degree of locomotion and what they're doing with that movement. So we'll start off here with locomotion traces, trails and trackways and footprints. They're called rapicnia. Those are locomotion traces. When the organism stops and rests and leaves its impression, it's called cubicnia, or a resting trace. Now, if this organism is buried by a sedimentation event and the organism escapes through the sediment, that is called a fugicnia, or escape trace. However, if the organism keeps up with sedimentation and sedimentation is steady and the seafloor builds up, we get an equilibrium trace. This is called equilibricnia. Now, if the structure is in one place through time and it's simple to more complex with multiple branching, these are dwelling traces, or domicnia. When the traces become more complex with multiple branching and components of vertical and shafts and tunnels, or they have sprighten, then these are called photonicnia, or feeding traces. Then there are more specialized traces that are called agricnia, that represent farming or gardening traces from the organism building a complex structure and then feeding off of that structure. And then we have systematic feeding and grazing structures, and those are called pasicnia. And then, of course, this wheel continues back to rapicnia. So it's various degrees of locomotion and what they're doing with it. So now, ichnology was started as a discipline in marine rocks and marine deposits. So let's take a look at marine systems and the biotic trends. The marine realm is enveloped in seawater, which is roughly 35 parts per thousand. So despite seafloor from the shoreline to the deepest depths and the input of sediment along the coastline, as we heard from Professor Simon Lang previously, the marine systems are relatively homogeneous, zonal, and uniform. That means light, depositional energy, nutrients, salinity, turbidity, sedimentation, temperature change are predictable to form benthic communities. So those changes through these physiographies are very predictable, and the benthic communities that form there are predictable. That's because in this tetrahedron of physical chemical controls, we see the major controls are depositional energy, sedimentation rate, oxygenation of bottom water and bottom sediments, and a variety of controls here in this corner, either medium, salinity, nutrients, hydrology, turbidity, or temperature. And these control the distribution of organisms in the seafloor and their terrain. It's also known as ecological stratification, and this is the vertical partitioning of benthic habitats of different feeding strategies and behaviors. So based on these patterns, the most important out of all of them is oxygenation, because unless the water is oxygenated and the bottom sediments are oxygenated, you will not have any bioturbation. And this bioturbation here, their distribution is controlled by the interaction of all four of these corners of the tetrahedron. So a very famous ichnologist by the name of Dolph Seilacher in 1967 came up with an ichnofacies scheme. This ichnofacies scheme is a recurrent pattern of trace fossil associations and sedimentary facies on a global scale through geologic time. The trace fossil associations represent physical chemical conditions that are operating on the trace-making organisms at that time on the seafloor. And the sedimentary facies, as Professor Lang showed us great examples, are the environmental and depositional controls at that time that they were constructed. So what we have here are a number of ichnofacies. Some are original from Silocker and others were added onto this, but we have Triponides, which is hard ground borings. We have Triatolides, which are borings in wood grounds, such as drowned forests or coals or peats. We have firm grounds, which is the Glossopharyngites ichnofacies. And you see these are mainly dwelling and feeding structures. And then we have soft ground ichnofacies represented by the Scalithos, Cruziana, Zoophycus, and Neurites ichnofacies. And these are controlled by various amounts of depositional energy and shifting sand, more stable, nutrient rich with finer grain sediments, then into deeper water settings where you get less and less oxygen, sedimentation, nutrients, and other impacts from shallower water settings. So we can actually see this predictable pattern of trace fossil association, sedimentary bases, depositional environments, physical chemical controls based on the distribution of behaviors and morphologies and feeding behaviors. Such in this part, we see that suspension feeding is the dominant form in these ichnofacies here because these are dominated by dwelling structures, but we have secondary feeding or deposit feeding structures here in these group, including wood eating by treated wood boring clams. But as we get to more stable parts of the environment, like the shelf and down to the slope, we have deposit feeding with secondarily suspension feeding and grazing. And then in the deepest waters, in the deepest parts of the basin, we have predominated gardening and grazing traces. All right, so a very clear pattern of distribution of trace-making organisms, traces, and sedimentary facies. Now, if we go to the continental realm, so continental systems and biotic trends, this is a very different creature. If you can see, the continental realm itself is basically engulfed in air. So we need oxygenated air, not only above the ground, but within the sediment profile above the water table. This is what makes up the continental realm. So the continental realm is quite heterogeneous and complex. And this reflects latitude, solar insolation, the amount of continentality, orographic effect, elevation, and climate, which creates a mosaic patchwork of aquatic and terrestrial communities, as we see here in a Whitaker diagram and our Holdrich life zones. So this spatial and temporal variability is recorded in the environments, the soil formation, hydrology, and the ecology and diversity of organisms. This heterogeneity and complexity is much greater than that's found in marine environments. And if we look here at our tetrahedron of physical chemical controls, we see similar categories as depositional energy, sedimentation rate, in this corner, either medium, salinity, nutrients, turbidity, temperature, oxygenation, but the big control here is the groundwater profile. This is what determines the distribution of organisms, and we'll talk more about this later on. And we'll see that these categories are reflected in a different way based on the continental types of depositional systems. So here is our more close-up of the continental realm. We can see that the landscapes and deposits are made up of alluvial fluvial environments, lacustrine, palustrine environments, and aeolian environments. And all these are strongly heterogeneous, where you have simultaneous terrestrial and aquatic conditions, and they can vary monthly, yearly, decadally, and it varied at other scales. But most importantly, any sub-area part that is stable for some amount of time, we get soil development. And soil development is a function of climate, organisms, parent material, relief, and time. Soil formation is the norm in terrestrial settings. So whether you're in contributory systems or distributary systems, the degree of soil formation and succession of soil types is significant, because this reflects the interplay between burrowing activity and soil processes with sedimentation and non-deposition periods. So this means that during non-steady deposition, or what looks like apparent steady deposition, the succession of soil successions or sedimentary successions in the continental realm can either produce no evidence of soil or a mixture of compound, composite, or cumulic paleosols being produced in fluvial or lacustrine above the water table conditions or aeolian. So how are organisms distributed in the continental realm? Well, we saw how they're distributed in the marine realm and what their control is, but the best way to illustrate this is using the work of Wallwork, and he classified organisms as epigean, geophiles, and geobionts. Where you live on the surface or above the surface, you're an epigeon. If you live and spend some part of your life cycle within the soil, you're a geophile. And if you spend the whole amount of your life cycle within the sediments, within soils, you are referred to as a geobiont. So these life cycles can either be hemimetabolists. This is basically what we are. Adult female lays an egg, the egg hatches, and it's a miniature adult, that miniature juvenile, which is basically an adult that grows into the adult form. Or you could be holometabolist, where the adult lays an egg, the egg hatches, the egg produces a larva. The larva lives for some period of time above or below the ground, and then goes into pupation stage, and then comes out through changes or metamorphism that produces the adult. The whole point is the more time that's spent within the soil or sediment, the greater degree of bioturbation and the depth of mixing. So let's go through these groups. So epigean are actually preserved in fossil records by their footprints, and with the diversity of footprints telling you the types of organisms and the number of footprints telling you their number and herd structures or how they travel in groups. Transient organisms are where the whole life cycle is above the ground, but only the adults are the ones that are in the ground for a short amount of time or a transient amount of time. They could be there for a few hours to up to several years. So examples here are stink beetle burrows or tiger beetle burrows, a variety of toad or spadefoot toad estivation burrows that they can be underground for 6 months to a year or more. And then lungfish estivation burrows where they've been known to be able to stay underground and then come to the surface when water returns after 3 years. Our next group are the temporary presence, where the adult lays the egg underground in a nest, and then the egg hatches and spends its time underground as a juvenile, then comes up to the surface as an adult. There are many representatives of this in modern and ancient. We have a variety of digger wasps. We have a variety of cicada nymphs and soil bug nymphs, a variety of dung beetle nests and balls and scarabaeid beetle larvae, and mass chafer beetles that live underground making burrows, and then even soil bees are part of this group. The next group involves a lot of social and eusocial organisms, and these are periodic, where you see the adults coming and going from the nest, or they could be found on the surface, but the whole of the life cycle and their dwellings are underground. So we have great examples of these. There are termite nests, there are ant nests that reflect this, prairie dog nests, wasp nests, and even crayfish burrows. Then our next group are the permanent dwellers, where you rarely, if ever, see any adults on the surface. The whole of the life cycles is underground, and these are represented by modern and ancient burrows. And here's the examples of the modern burrows, like mole burrows, vole burrows, naked mole rats, trapdoor spiders, and earthworms. So what controls their presence in the soil? Well, that goes back to our groundwater profile and its seasonality. All right, so we can look at the groundwater profile, and at any one place, we have the vadose zone or the phreatic zone. It's also known as the unsaturated zone and the saturated zone. This depth of this creates accommodation and allows the organisms to burrow to certain degrees of depth based on the amount of soil moisture present and the depth of the water table. This is also reflected in the lateral variability of the landscape, because as you get closer to an open body of water like a river or lake, the zones become compressed, accommodation decreases until the groundwater table is above the ground surface to form a lake or river. And there you get a different suite of organisms and different suite of traces. So if we look at the depth and the distribution and diversity of organisms and their traces, we see that that changes based on where you are on the floodplain, from distal to proximal to transitional to wetter environments to then lacustrine or fluvial channel environments where we don't see deep burrowing at all. So in general, this is a great comparison we put together. If we look at the depth of the variety of burrows and nests and the penetrative traces made by organisms, termites can make nests that go down 100 meters. All right, plant roots have been traced down to 65 meters. Ant nests only go down to about 15 meters. Freshwater crayfish, and particularly from Australia, could go down 9 meters to the water table. And then most organisms in their bioturbation is within 5 meters of the soil surface or sediment surface. Now, if we compare this to freshwater aquatic settings, or hydrophilic, like in rivers or lakes, the vast majority of organisms burrow within the top 10 centimeters of the sediments underwater, with very few making deeper burrows, like around 50 centimeters. All right, so this is strikingly important and significant because you get a greater degree of mixing and penetration in the terrestrial setting compared to the freshwater aquatic setting. All right, so the presence in soil or sediment, the tiering and the depth of bioturbation or sediment mixing and soil formation are controlled by the groundwater profile. So the distribution of trace fossils and traces are not controlled by facies or facies associations like they are in marine ichnofacies. Therefore, only the original Scoiania ichnofacies, as defined by Silocker in 1967, is recognized as legitimate. All the other proposed ichnofacies fall apart because they don't follow any trends and don't give us any important information about the environment, the hydrology, the ecology, or the strategies for feeding and reproduction. But all is not lost, because we could take this information from continental and marine trace fossils and ichnology, and we can integrate them with sedimentary facies to learn about our ancient world. And we can categorize those into academic interests and industry interests. But if you notice that they're pretty much one and the same. One is for academic and evolutionary pursuits and basic interpretations, and others are for applying those interpretations and in understanding our reservoirs and seals and geometries. And we do this by looking at the trace fossil and its relationship with the lithofacies in said structures, the tiering of those traces with respects to bed and bed sets, and then how those trace fossils and their tiering are related to facies associations and geometries, stratal architectures and sequences, stacking patterns and sequence sets, all the way up to how they change through the basin fill successions. So in academia, we're interested in things like behavior, hidden biodiversity, proxies for communities, groundwater profiles, soil environments, soil formation, local climates, and then greater reconstructions of landscapes and seascapes, biomes, regional climates, extinctions, and so on and so forth. On the industry side, some of the basic questions need to be answered. Is this marine or continental? So what's the sub-environment? What are the sedimentation rates or accumulation rates? What's the redox profile? What can we learn about reservoir quality and fluid transmissibility, KV and KH? What can we learn about reservoir and seal geometries, continuities, and connectivities, and so forth? So the remainder of the talk, I'm going to show you some examples from modern and ancient sedimentary systems where we can use the interplay between traces and facies to define new facies associations in models, use burrows as indicators of biodiversity and groundwater table and sequence boundaries, and look at burrows at high and low paleolatitude and integrate them with facies to interpret environments of deposition, ecosystems, and changes in climate and sequence stratigraphy. All right, so the first example are terminal splay complexes in Lake Erie in Australia. And this is work I did with Simon Lang. We started out in on the west side of Lake Erie North with the Niels, Umbum, and Douglas terminal splay complexes. And when Simon left and went into industry, the remaining group came and studied the Kalawirna terminal splay complex. And we came to this area, and there was just in flood. And here where it floods, unlike what happens in some of the parts of India, that the splays just make it to the river, to lake margin here, which is dry. And then the flood waters just sort of trickle out onto the lake margin and just infiltrate. So we were cutting trenches here to look at what the three-dimensional sediment packages of these terminal splay complexes represent below the dry lake floor. And what we found was quite astounding. We had a variety of burrows that looked like marine traces and a variety of sediments that included sand, mud bundling in couplets, reactivation surfaces. We had flasier, wavy, and lenticular bedding, large mud cracks, all combined would suggest you're in a shallow marine setting with lunar generated tides. But we know we're in a lake setting. So how do you get these very distinctive tidal signatures with this type of traces found with them? Well, we discovered while we were out there that these are wind generated tides, not lunar. So the diurnal change of the heating differential between the lake bed and the landscape created changes in the wind twice a day that would blow the flood waters into the lake basin and then blow them back in the other direction to produce these tidal signatures. And also interesting, these traces weren't made while these waters are there. These are terrestrial traces. These are traces made by spiders, these vertical tubes that can be interpreted as scalithos, by simple root patterns that resemble chondrites, and these are made by saline-tolerant plants, and this modified nests of ants that look like the trace fossil gyrolithes. So what we were able to do is produce a new facies model for dry land lacustrine or lake systems that have these fluvial influence from terminal splay complexes. In our next example, we could use crayfish burrows, which are proxies for biodiversity, groundwater, and more. And this work we did in Kansas, here in the US, right by the University of Kansas. So this is a crayfish, and people think crayfish just live in water bodies, but many of them actually live in burrows on floodplains. And they do burrow in lakes and ponds, but they're very shallow and very short. But what we did is we found a number of crayfish burrows in this wooded wetland and followed them out into this wetland savanna transition and onto the savanna. And we poured resin into a number of burrows from the wetland out to the savanna, and then we excavated them. And what we found that here in the area of the spring, we had no crayfish or their burrows. But as we got away from the spring, we started getting burrows. And these are the casts of those burrows in the relative position. But way out in the savanna, the burrows, which represents here, were down to 2.5 or 3 meters in depth. And you can see there's the groundwater table here that actually came up when we opened up this burrow hole, this hole where the burrow is, and there's the cast of that burrow. So what's significant about this is we know that the regional groundwater table is between 6 and 8 meters deep based on our hydrologic station that is right nearby this study area. So what we see is that the crayfish burrows represent a perched water table that's fed by the spring. So this is significant in that we can use the burrows themselves based on our modern work to say that they mark the position of a water table or perched water table, and that their complexity and architecture is greater where the water table is close to the surface, like 70 centimeters or less, versus when the water tables are deeper, 2 to 3 meters deep, and they're very simple where they burrow from the ground surface down to the water table. So we could take the same information and look at burrows on the Upper Triassic Chinle Formation, which is about 220 million years old on the Colorado Plateau, and we could see the same patterns in burrows that I've interpreted as being crayfish. So here, and note the lens cap here, 5 centimeters diameter. There is that same lens cap here. You see that where the burrows are much more complex, multiple openings, big chambers. The water table is likely very close to the surface and doesn't fluctuate much. But where the burrows are very deep and very long, 2, 3, 4, 5 meters in depth here in the Chinle, that reflects the deeper, more fluctuating water table. This is substantiated also by the soil structures and the redoxomorphic coloration you see here. And if you also note here, the whole of the landscape has multiple generations of crayfish burrows that have actually produced this soil. So tens to hundreds of generations. It's a very stable landscape. So out of millions of burrows that we examined, we only found a handful that had crayfish fossils in the bottom. So based on the comparison of the architectural and superficial morphology of these burrows, we know that they're crayfish, and we are able to find body fossils in them. So these burrows are proxies for the body fossil record of freshwater and terrestrial crayfish. They're also a proxy for paleosols, and we can use them as a proxy to understand the paleohydrology and reconstruct the paleo groundwater table and understand the seasonality of precipitation and the seasonality of climate. We can also use these to understand sequence boundaries and determine sequence boundaries. So here's the example from the Chinle Formation, and this is the base of the Chinle. The Chinle is Upper Triassic in age. It overlies the lower to middle Triassic Moenkopi Formation. And what we find that there are major incised valleys and interfluves that are part of the Shinnerup member of the Chinle Formation, and its equivalent, which is called the mottled strata, which is found on the interfluves. And what we see here is that the penetrative crayfish burrows and the paleosols in the interfluves here are actually have incorporated the uppermost part of the Moenkopi. So there's the Chinle proper, but this part was part of the Moenkopi Formation, but because of the bioturbation by the crayfish and by soils structure modification and rooting, this part of the Moenkopi now has become part of the Chinle Formation because its modification is Upper Triassic rather than Middle Triassic. So Middle Triassic sediments are the parent material, and Upper Triassic activity modified that. And in other parts in the bottom of these big interfluves, there's the Moenkopi Formation, and then these are the crayfish burrows that lived on that surface and that were filled by Shinnerup sediments. So these are major sequence boundaries that can be traced over tens of kilometers to hundreds of kilometers on the Colorado Plateau. All right, so our next example comes from the North Slope of Alaska. This is the Schrader Bluff and Prince Creek formations at Shivigak Bluff, the North Slope of Alaska. And here, the study was to look at this important outcrop analog, which is in the Schrader Bluff and Prince Creek, for subsurface oil-bearing reservoirs in the National Petroleum Reserve of Alaska that runs along the Colville River. And we studied the outcrops along this National Petroleum Reserve of Alaska to better understand this analog. The earliest work that had been done here found that most of the section was covered and that they determined that below the mid-Campanian unconformity is mostly marine or all marine deposits, shore-faced deposits, and above this unconformity or sequence boundary were continental deposits of the Prince Creek. What we ended up doing is a lot of detailed trenching and cleaning off of the outcrop for tens and tens of meters so we can get a centimeter by centimeter analysis of those covered intervals up to the sequence, that main sequence boundary and above. And we're able to determine that there's not just one large marine section below the mid-Campanian unconformity. What we found is an overall shoaling upward succession of distal to proximal deltaic deposits, like those shown by Professor Lang, all the way up to delta plane deposits on top of the section above the MCU, so that the Schrader Bluff was basically complex deltaic deposits and that the Prince Creek were part of the delta plane deposits. We found ichnofacies that represented the Cruziana, Scalithos, and Scoiania ichnofacies, and that these ichnofacies with the sediments recorded variations in the depositional energy, sedimentation rate, oxygenation, groundwater profile, media consistency, and even places where you got subaerial exposure. So this integrated approach demonstrates the presence in this area of several sequence boundaries that reflect sea level changes below this mid-Campanian unconformity. So here are some of the examples. Moving up through the section, we determined that this part here was part of the Cruziana ichnofacies, represented by these feeding traces of phycosiphon, Tychicnus, and you can see the spriton here, and Rhizocorallium with the spriton here in the middle. But further up the section, this changed to traces and more sandier sediments that represented shifting higher energy. So we got macronicnus, where these are feeding wholly within sand, and conicnus, which are basically suspension feeding organisms. So the ichnofacies shows us higher energy and shifting sediments and the change in those ichnofacies. And then further above that Scalithos ichnofacies went back to the Cruziana ichnofacies, which are represented by Astrosoma and Planalides here, Phycosiphon and Schab cylindricnus, and Helminthopsis with the sinusoidal feeding trace on the surface. But going up section, we incurred an interval that had facies associations and traces that are tied to continental types of deposition with hadrosaur undertracts or dinosaur undertracts, variety of rhizoliths, rhizocretians, and rhizohalos, and terrestrial traces that are indicative of the Scoiania ichnofacies. And then above this, we had a major flooding to the point where we were back to marine deposits and facies associations back to the Cruziana ichnofacies. So within this succession, at one time is seen as just as one large shore face that was shoaling upward to a coast, to a strand plane. It's actually deltaic deposits with multiple sea level rise and falls within this interval. All right. So our next example takes us to Antarctica, to the Permo-Triassic boundary, the Beardmore Glacier. And the purpose of our study there was to look at the Permo-Triassic transition and determine what, if any, extinction indicators were recorded by trace fossils across this boundary in Antarctica. Most of the work had been done by great scientists in low latitude settings, but we wanted to know what would be recorded in high latitude settings in continental environments. So here's an example of the outcrop. There is the Permo-Triassic boundary, and here's a scale for 25 meters. So these are vast, vast outcrops. What's really important is if we look at present day climate, Antarctica is covered in ice. And the biodiversity is very different compared to when it was in the Permian, the late Permian to Triassic, where Antarctica was in a similar position, but the climates were much warmer at that time. So what did we learn from our research there? Well, as a quick summary, going from the Buckley Formation, which is late Permian, into the Fremont Formation, which is early Triassic, we saw in the Buckley the representation of poorly drained landscapes with abundant ground cover based on carbonaceous rhizoliths, coal seams, and drab colors, and lots of fluvial and palustrine deposits. We had very few traces of vertebrates and terrestrial invertebrates, but we had an abundant and diverse aquatic fauna and flora in lakes and swamps based on the variety of trace fossils we found there. For example, these are fish swimming traces here, and there's an example of a modern one. We had in situ tree stumps with very shallow lateral roots, so we know the water table is very close to the surface, and these are partly inundated during the year, and then these are covered by deposits of shallow lakes. But we also saw, based on evidence of burnt wood in these Permian deposits, like we see here in the modern examples, that there were recurrent forest fires that signaled increasing seasonality and moisture that were available, something like we see in present day northern parts of North America, like in Alaska. So you cross the boundary, and in the Triassic, almost immediately we see well-drained landscapes with abundant ground cover based on rhizoliths and redoxomorphic features that were quite deep, almost up to a meter in depth. We also found evidence of diverse archosaurs, therapsids, and other vertebrates based on their footprints, as well as abundant vertebrate burrows within 1 to 2 meters of the boundary itself, and of course further up in the Fremont Formation. And we also found abundant and diverse aquatic fauna and flora, such as algae, in the rivers and ponds. So if anything, there was a greater diversity in the Triassic compared to the Permian. What's the take-home message with that? Well, the integration of the traces and the facies shows us that there was a major hydroclimate shift across this PT boundary, in that there was a major improvement in drainage that controlled the distribution of facies and biota. There are abundant terrestrial and freshwater traces that are similar in diversity and abundance to Permo-Triassic units in the northern hemisphere. So what we found in the southern hemisphere is very similar at the bottom of the world to what we find here in the northern hemisphere. Such ichnotaxa as Cruficnium, made by horseshoe crabs, Undicnia, made by fish, and a variety of fierce traces made by insects called Pherocycnus. These were globally distributed on land by the late Permian into the early Triassic. So we saw little difference between high and low latitudes in terms of ichthyodiversity in continental settings. And more importantly, the mass extinction didn't seem to be as severe at higher latitudes as it was at lower latitudes and marine intervals. This is significant because the PT boundary marks the time when 95% of life on Earth went extinct. So it seems that in higher latitudes, this extinction was not as severe. So that means potentially that high latitude polar environments at that time, late Permian, early Triassic, served as refugia for terrestrial and freshwater water communities. Okay, and then in our last example, we did a study on the traces and paleosols in Wyoming to look at changes in landscape, drainage, communities, and climate. And the question we asked is, how did these rapid transient warming across the Paleocene Eocene thermal maximum, a rapid warming of 4 to 7 degrees centigrade, how did this affect communities and landscapes in Wyoming? This is a very pertinent question because many people think we're going through major rapid global warming now. Well, if you want to know the answer to what might happen today, we actually have examples of this in the rock record. And we have a good example of this in the Willwood Formation in the Eocene of Wyoming. And here's where the PETM is represented in outcrop. It's this thick red interval. So what we did is we took information from our paleosols and the traces of invertebrates and vertebrates and the traces of roots and the coloration of the soils. And we looked at how those changed up section through the Paleocene Eocene thermal maximum, which is this interval here in pink. And we already know that based on the CO2 from the marine record, as well as the proxies from soil carbonates here, that we could see the trend of the elevated CO2. So we could use all this information then to interrogate our geologic data to see what pattern took place. So we wanted to interpret changes in paleosol maturity, drainage conditions, trace fossil community, also known as ichnosynosis, and the body size of organisms based on the diameter of a trace to evaluate the effects of this rapid climate change. So what we found is that we saw a clustering of different types of drainage conditions with paleosols and trace fossil communities or ichnocynoses. And these are pretty much color coded, where the reds and purple dominated soil colors are better drained soils, whereas the grays and olive greens and yellows were more poorly drained soils. So what we found was the pattern is very striking. This was pre-PETM, so we have more drab colored soils than we do red soils. But during the PETM, we get more and more better drained red and purple color soils, and then almost back to the more natural background after the PETM. So when we combine all of this information plus information from the study of burrow diameters across the PETM, so this one is for Nactodomasis, this is for Scalithos, and this is for Planolides, we saw that the ichthyosynoses record improved drainage conditions of the landscape through the PETM. Simultaneous with this, we can see that here in the estimated drainage conditions. Simultaneous with this, we saw changes in the trace fossil communities with either losses or gains in the membership based on the drainage conditions. And probably most importantly, we found that the ichnotaxon, these paleosols, recorded a decrease in the body size of the organisms by 40 to 50%. And this is significant because previous study many years ago on the vertebrates based on the teeth of mammals saw a decrease of 40 to 50% of body size. So it begs the question, why? Well, this is because of the higher CO2 levels. So for the soil organisms that were mostly invertebrates and mostly insects, higher temperature leads to lower relative humidity and lower quality in the vegetation, which means smaller body sizes, earlier sexual maturity. Earlier sexual maturity means producing young with a smaller body size and at an adult smaller body size. So this explains the pattern that we see across the PETM. So rapid warming doesn't really create mass extinctions, but what it does create are changes to the communities and the individuals for their body size and the community structure. So with that, I'd like to conclude that ichnology plays a significant role in interpreting autogenic and allogenic processes in the rock record. Ichnology isn't the center of the universe, but it is the center for interpreting various sedimentary and climatic and evolutionary and hydrologic processes that can be used to infer us about climate. And then we can tie those together with bigger changes in basin fill and changes in paleogeography, and help us understand relative changes in time through the sedimentary succession. So trace fossils are proxies for micro to megascopic diversity. They preserve these organism media interactions that record important physical chemical factors that control diversity and distribution of organisms in the landscape and seascapes. We use the succession of traces with the sediments to interpret sedimentation rate, depositional energy, oxygenation, and other metrics that are used to interpret environments of deposition. And in places where people have already described the paleoenvironments, we can go in with the ichnology to refine paleoenvironmental, paleohydrologic, and paleoclimatic interpretations and make more accurate reconstructions of the past that can be used for academic pursuits as well as industry pursuits. So with that, I thank you very much for your time and your patience.
Thanks a lot, Stephen. It looks amazingly complicated with a lot of science and interconnection things. And it's amazing. I didn't even know that such a complicated area of looking at it. So definitely thank you. It was so amazing that such a science has evolved that looks into all these details and also connects the various other groups together, as you have shown. Definitely, just looking at rocks, but looking at it from this angle gives a different viewpoint and adds on to making that uncertain model more certain, isn't it, with all these things? So with that, let me open it to questions. Maybe only one or two questions. Anyone? Is it a question? Somebody, I can hear somebody talking.
I don't think that was a question.
Oh, that was just a noise.
It's time for dinner, I think.
So one question I had while others are thinking about questions is, how much time does typically one of these studies take? Because it involves a little bit of digging, looking at things, and there can be so many things. You must be using microscopes at the same time to look at the finer scale things. You have to put resins, as you said. So all this would take quite a bit of time, isn't it? One study of a certain area?
Actually, that's a fantastic question. A lot of these studies, you would think take several years, 2, 3, 4 years, but what's incredible is they're actually continuous. So for example, the crayfish studies I began when I was doing my master's and my PhD, but I continue that work with more research and more data to refine the interpretations and understand how then they can be used to infer more aspects of ancient climate and hydrology. So some of these studies still are lasting 10, 15 years because they're additive and add to the data set. So like, for example, one thing I didn't talk about is I studied modern acid mine drainage with a colleague at Indiana State University. And that study has been going on now for 22 years. And we're still learning more and building on what we're learning from that acid mine drainage. So what we've done there, we mentioned microscopes, collected live samples, watch the behavior under microscope, use SEM to SEM the biolaminate or the biofilm itself, and then SEM the various portions of the banded iron, modern banded iron that they're creating through their behaviors, and finding that in this case, the biggest constructor happens to be the protozoan Euglena mutabilis, because of this acid drain. The waters are so acidic between 1 and pH of 1 and pH of 4. Right, so this is very long ongoing studies. I'm still doing research with fossil termite nests and modern termite nests, and working with Simon Lang in the northwest part of Australia to understand how termite nests and their distribution reflect the climate and the environments of deposition in arid settings versus more tropical settings or subtropical settings, and how that might reflect those types of depositional systems where you have large sheet floods and large floods under conditions of very seasonal and small amounts of precipitation. So this work is, almost generational, and hopefully, all these young people who are tuning in, and young people like us who are tuning in, who can carry the torch and keep doing this research, because there's so much to learn, and these are always ongoing. I think if you said, and most people would agree, like with your presentation, that if you think we learned everything already, we haven't learned enough. We must keep looking at, our areas of research and study to understand better. If you do one thing, what happens when you do that? How does it affect another? All right.
Correct. Yeah.
Thank you very much, Steve. As usual, that was a great talk.
Yeah.
A lot of information. And every time when I hear you, that's like a lot of new stuff, new things are there. So always I was thinking about when you showed some of these organisms, burrows and all of that in the present day, or at the time of the deposition, or maybe in a shallow depth, what will be the size of the body? If you see that in a record, like around 2,000 meters to 3,000 meters down, when you get into a core, what will be the ratio? Usually you see 1:2, 1:10. So what type of ratio you see with the body or the size?
Well, that's a great question, Saju, and that depends. That depends on the grain size of the sediment and the environment in which that sediment was deposited in. So it's a very good question. So, for example, if you're in terrestrial settings where you have paleosols, and let me see if I can go back to this one picture here. Where you have paleosols, these are gravitationally drained, right? So the compaction on a paleosol wouldn't be like that of a mudstone in a pro-delta, where you might have a compaction of 8 times or 4 times or 5 times or 8 times, or to the abyssal plain where it's all mud, where you might have compaction of 1 to 9, so it's 9 times. In this case, paleosols sometimes have a compaction of 1.5 or 1.8. So they don't compact much more because they're already gravitationally drained. And when you add more sediment atop them, they're also gravitationally drained, and they're compacted through the petagenesis. So you don't have much in the way of compaction there. So in some cases, some people think there's almost no compaction on some of these soils because they're well drained. Now, if you have a poorly drained soil, if they're clay rich, and those clay rich parts don't go through any gravitational drainage, then you might have compaction of 2 times or 3 times. But most of these soils are pretty much gravitationally drained, and they don't compact much. Lacustrine sediments, they will compact much more because they're not gravitationally drained, and they're subaqueous. So a lot of these will have compaction rates similar to what we have in the marine realm until we get into the terrestrial deposits, which don't seem to have a great amount of compaction to them. So they're much smaller than you would have in the marine setting. And marine settings are more standard for compaction, which would then affect the burrow diameter ratios.
Thank you. That's a good answer to my question. And thank you very much for accepting and giving a great talk in our online conference. Much appreciated.
Yeah. So I think we are getting late. And if there's any other last question from anyone, we can take one last question.
I see a question here in the chat. They wanted to know if it could be used for age dating.
Yes.
So what's really interesting, we can use them for relative age dating, meaning that was there slow sediment accumulation or fast sediment accumulation, or were there periods of no accumulation? So the greater degree of bioturbation and greater depth and the greater amount of soil formation shows that there is more time that's tied into those deposits with that bioturbation and those soil structures. So depending on the maturity of that soil, they can represent hundreds to thousands of years to actually millions of years. The other good thing about trace fossils are they can be containers for ashfall deposits, where you might have ash deposits on land, but when they fill burrows, you have that ash contained. So if you remove the ash from the surface of the landscape or seascape and preserve it in the burrow, that could be a vessel for getting absolute age dates. So you would look for zircons and other things in the ash within that burrow fill. So burrows could help preserve ash for absolute age dating. So they're mostly used for relative age dating, and we can get relative standards that then we can compare to modern soils, for example, where we know that, oh, this soil is 40,000 years old with these features, or this soil is 80,000 years old with this features, or many of those in Africa and some in Australia, where they represent 1 million or 2 million years of age. So when we do that comparative analysis, we can say that, oh, okay, this succession with these traces and these soil features, we know that this is roughly 1 million years, or 10 to the 6, or this is 10 to the 4. So that's how we can use it to get relative and absolute ages.
Good. Thank you, Steve, for beautiful presentation. Very different from all presentations we have heard. So
Well,
really, that was good. Yes. So with that, yeah, very nice. Thanks. So thank you to all the speakers who gave talk in these sessions, and we thank the audience for some of the questions and being alert to digest all this varied amount of presentations we had in these times. Saju, anything else to add?
We know nothing. We can give back to Christ College. Then they will give a concluding remarks.
So over to Christ College. Thanks.
Thank you, Dr. Saju and Zach Jones. Am I audible?
Yeah, we can hear you.
Okay, thank you. Well, thank you very much. Today we had very interesting sessions, especially the last ones, and also, of course, the 3 talks that was specifically on geoscience, and one on the big data analysis. It was very well received, and I'm really glad that our participants stayed with us, even though it was little late. As rightly said by Stephen, only with a lot of passion that we will be able to take up this journey forward. And I'm sure that is the reason we are all here. And all of us are young enough to do this, as rightly said. So I congratulate all the participants that you chose to be here with us today. And I'm sure that you have learned a lot. And I wish you all the best. If any one of you or few of you take up geology as your higher research option or further research, that would declare that this program was a success. So thank you all the session chairs today for taking time and pain, though it is very late, I'm aware, at your end. You are staying with us. So thank you so much. And now I request Ms. Asha to conclude the session. Thank you once again.
Okay, so that brings an end to the 7th International Geoscience Colloquium. And let me thank our session chairs, Dr. Saju Menacheri and Mr. Zach John, for handling the session very well. It gives us immense pleasure to know that we have attracted global audience and provided you all an opportunity to discuss geoscience. Christ College Autonomous, on behalf of the organizing team, thank each and every one of you for your active participation. And let me remind you that we have provided the feedback link for the participants. Please fill it, and we will get back to you soon with your certificates. So until we meet for the next time, it's a goodbye from all of us. Thank you.
See you. Bye.